Huh. Now
Yeah,
I should be
we are
able
to see.
Yeah, let me see. I have to be able to set up. There's just too many things going on here. I have to close many things. Oh. So today is okay. Loudness and pitch. So you should be seeing something, right?
Yes, yes.
Okay,
I
good.
think yesterday's last slide or something.
Yes, yeah. I just wanted to remind people what we were talking about. And
yeah.
So, how many people are we still having? Do you have any idea?
About 75.
Oh, still, this is crazy. Are they all coming, getting up, or?
Yeah, yeah. I think maybe another minute or two.
Yeah, most of them I don't know, but
yes, yes.
is
yes.
it Pratibha Jain?
No, no, no.
No, it's Pratibha
Pratibha Jain,
RJ.
yes.
Is somebody else? Yeah, okay. This is not my former
Yes,
student.
yes.
Okay.
So you may know the sad news. Pratibha's father passed away recently.
Oh, I don't know. No, I'm sorry to hear that. Yeah.
Yeah, yeah. I contacted her for something. She told she's busy with these rituals and those things. Then
I can
I came to
imagine. Yeah, yeah.
know.
So actually, it is a time to start slowly, right?
Yeah, yeah. We'll start the Henrik.
Okay.
Yes. Let us go ahead then.
Zastavuju kameru.
This meeting is being recorded.
So this is just by the way of reminding you what we were talking about yesterday. In the first half of the talk, we talk about auditory cortex, and just try to remind you that hearing is not just the ear, what we are seeing when you look at a person, or even the periphery, what's happening inside the ear, but hearing is the whole complex system, and signals from the ear.
You have switched off your camera, Henrik.
Well, I can do it, but we are just getting up here, so I don't want to do that. You know,
Okay.
Do people
Okay.
have to see
No
me,
problem.
or
Please, please.
I can do
No,
that
not yet,
eventually. Yeah, I will do it.
Yeah.
I'm aware that the camera
Thank
is
you.
off because it's early morning here, you know, and
Yes.
maybe we can discuss eventually if we can switch at least my talks for about an hour later, because it's becoming too early here.
Yes, yes.
The whole
Okay.
place is just getting up. I can get up, but my wife sometimes still sleeps. And anyways, it's okay. But I will switch on the camera the moment
Yeah,
the whole thing is gets organized here. Okay, so
please.
we talk about hearing, and actually we talk about what is called wetware of hearing, physiology of hearing, what is happening inside physiologically. And so yesterday I was talking about the more important. Every part of the hearing is important, but about the important part of the hearing system, which is the auditory cortex, the brain, which is processing data. And as I just told you, it's not there is not as much known about the brain as there is about the ear, but the little we know about is still very interesting. So main thing which we want to remember is, I try to summarize it on this slide. If the ear is separating acoustic components of acoustic signal into different frequency channels through the selective action of the periphery, this organization, these frequency channels, keep continuing all the way to the brain. In auditory cortex, we are finding the parts of the cortex which are differently sensitive to different frequency components. The same, by the way, the frequency components of the signal are getting separated in the ear. So different parts of the auditory cortex are sensitive to different frequencies of the signal. This is called a tonotopic organization of the cortex. And we will refer to that later when when we will be thinking about some alternative ways of processing of the signals. And but also that another interesting thing is that when we are looking, well, ear or the whole neural system is communicating mainly through what is called action potentials, the spikes. And the spiking starts, in the case of hearing, starts on the level in the ear, and on the level of auditory nerve. This is the wire which is going out of auditory cortex, or sorry, of the ear up to the higher levels. The firing is of the order of 1 kilohertz. Every millisecond, there seems to be a spike or so on most of auditory nerves. Then there is a number of auditory nerves. There may be tens of thousands of fibers in auditory nerves. But we have some idea what is the width of the communication channel. But this communication channel is getting broader and broader. Let me just switch on the video. Maybe it's getting broader and broader towards the higher levels, and so a number of neurons is increasing while the firing rates are decreasing. So all the way to the cortex, then at the cortex, firing is slow, relatively slow. I mean, maybe several spikes a second. Of the order of tens of spikes, tens of hertz, but the number of neurons is much huger. So we don't know exactly. Nobody can count it like this, but by the estimates, there may be as many as 100,000 of neurons on the level of auditory cortex. Also, most of the unlike the neurons on the auditory nerve or in the periphery, where all of them are pretty much busy, on the level of the auditory cortex, just a few neurons are busy, maybe 5 to 10%. The neurons are doing nothing. Well, nothing. They are certainly not emitting signals. So this because these neurons are highly specialized at the higher levels, and if the type of the signal is not such that it's interesting to this 90% of the neurons, these neurons are doing nothing. They are just quite happy to be resting, ready to fire only when a special type of the signal comes. And we were talking about it, and higher and higher levels, the neurons are specialized, more and more specialized. Level of the periphery, pretty much the sinusoidal pure signals are kicking off the firing of the neurons. On the level of auditory cortex, sinusoids don't really do much to cortex. I mean, you have to at least switch them on and off in order to have to create a little bit of excitement for these neurons. So essentially, where the first hour we ended up, that it seems that our auditory brain has many ways of looking at the signal. And that answers also maybe some questions when we are looking at the signal and we see that there is so many different types of the spectrotemporal patterns. And we are sort of almost wondering and say, maybe we would like to just use more than one Fourier transform of 10 millisecond. Because yes, indeed, that's what auditory cortex seems to be able to do. It seems to be able to look through various color glasses at the world. And actually, how many color glasses, how many ways of looking, it may be millions. So this is a good to remember. So that was about the cortex. If somebody has asked any questions about the auditory cortex, which you were shy to ask yesterday, now it would be a good time to ask. Okay, if not, then I will switch. I will go a little bit further. And then next hour, we went to what is called the psychophysics. Psychophysics is dealing with not what's happened, what is inside, not about the elements of the system, but what the system is doing and what the whole system is doing. Psychophysics is what the psychophysics is doing is that you give a system a stimulus and you are asking the system what kind of effect it has. And of course, how do we ask is that in case of human beings, we present the signals and we ask people what do they hear. And there's a whole series of skills how to ask the right questions. But the simple question which we spent our time on yesterday was the threshold. Do you hear something or don't you hear anything? So you are sending the signals which may not be creating a sensation, and you are increasing the amount of excitation in a certain direction. And at a certain point, people start hearing. The simple thing is that you are asking, can you even hear anything? So you are setting a signal of certain frequency and you cranking up the volume. And at a certain point, there is a threshold is reached. The auditory neurons start firing, people start hearing the sound. So you discover the threshold, and just looking at the thresholds, we reveal a number of interesting things about the hearing. And one of the most important things which we talked about yesterday is the masking. Masking seems to be pretty kind of straightforward thing. It means that if you have the more than one component to the sound, one component maybe mask the other component, so that certain components are stop being heard, be it in frequency or being in time. But when we look at it carefully, we discover a lot about the system. We discovered during a simultaneous masking, which is the masking which happens at the same time. There is a masker and the signal happens at the same time. We discover that the maskers, which are stronger, are always heard, are masking the signal only within the certain frequency range. This frequency range is called critical band. Of course, it's not a band like a square band, but it has a certain shapes. But most importantly, from our point of view, is that certain components do not seem to be disturbed by other components. That's the important thing. So even when you hear the masker, if the masker is far away in the frequency, no matter how strong it is, the signal in other part of the frequency spectrum is still being recorded. You still hear it in presence of the masker. While if the masker is getting closer and closer to the signal, eventually it starts masking and you don't hear the signal. So this is interesting. If you think about the robustness, of course, that tells you that some components of the signal may not be obscuring in terms of the detection the other components of the signal, no matter how loud the sound is. So as long as the disturbing sound is limited, is isolated in the frequencies, it doesn't cover all frequencies of the spectrum. It's very likely that some of the signal from some of the components of the signal, maybe that may be the speech, are still being decoded. Very, very interesting phenomenon if you think about it. So shape of the filters is one thing, but the principle that some components do not interfere with detection of other components, this is the important thing to remember. And we also talk about an even more interesting phenomenon, which was called the co-modulation masking release. If the components of the masker which is masking the signal are all changing with the same speed, they are co-modulated. Stronger, the more components we are providing, less masking is happening. So this is pretty much amazing, because that means that the brain, auditory brain, is so smart to this. The more evidence you are providing about the components of the disturbing signal, easier it is for the ear to ignore them. So I spent only a couple of slides on that, because as we agreed, in these lectures, those are not the lectures on psychophysics of hearing. Those are lectures for to know a little bit about hearing for engineers who are interested in processing of auditory signals. But if you are more interested in that, I strongly encourage you to look at it if you start thinking about robustness in presence of noise. And we also talked then about another phenomenon, which is a forward masking. Forward masking happens when the masker happens before the signal. An interesting thing there was, again, I mean, in a certain temporal interval of about syllable length, about a couple of 100 milliseconds to 300 milliseconds, effect of the masker remains, stays, and it's still masking the signal. This points to another thing besides the having this critical bands in frequency. We seem to have some I call it critical time interval in time, which is about the syllable length, which is telling you whatever happens inside this critical interval interacts, just like the frequency components within the critical band interact. Components within the critical time interval in time also interact. But once the masker of the masker system seems to be like, forget about the masker. There is a little bit of also masking going backwards. When the masker happens after the signal, there is still some effect, but this effect lasts for shorter time, for about 50 milliseconds. And some people say that maybe the mechanism is even different. It's more like on cognitive level. The system gets a little bit, goes into the shock. Professor Brian Moore from Cambridge claims that he could unlearn the backward masking. Basically, by forward masking, you cannot unlearn. Basically, it's there and the system gets affected. But for backward masking, you seem to be able to ignore it. I don't know, but forward masking to me is more interesting. So this is what we talked about yesterday. We talk about the critical bands. This is an important thing, which is critical bands of hearing are narrower at the lower frequencies and are getting broader and broader towards the higher frequencies. And they are seen through the number of mechanisms. The masking curves, I copied it from Zwicker. These are the masking curves of critical bands. You can see what's happening is as the masker is getting stronger and stronger, there is more masking. And this is masking is spreads towards the higher frequencies through the action of the basilar membrane, because the lower frequencies excite the whole basilar membrane, while higher frequencies only excite a part of the basilar membrane. So the masking pattern spreads towards the higher frequencies. These are the tuning curves. So these two things are related. This is how the system is filtering, and you can see that the tuning curves are having shallower shapes towards the lower frequencies. Subsequently, the masking spreads towards the higher frequencies. And we can sort of think about coming with emulating these the filters through engineering. This is one of the examples I found somewhere, how you can emulate the auditory filter. You can see auditory, if you knew how to measure the relative intensity of the sound, you could even make these filters adaptive, just like in reality, that as the signal is getting stronger, the lower part of the filter is getting shallower, while the higher part of the filter stays the same. In I'm not aware of any system which get the advantage of having these filters adaptive, but who knows? This clearly it's happening in the physiology, and we may think about it. And so this is the critical filters, and just to remind you what we have observed about the critical time interval. Interval is about a couple of 100 milliseconds. Effect of the mask is gradually decaying up to about 200 milliseconds. Interesting thing is, if the mask becomes stronger, then the decay is becoming faster, so that either way, if masker is stronger, there is more masking at the beginning, but it decays faster than if the masker is weaker. So the phenomenon is quite nonlinear, been studied quite a lot. Okay, how much time I spent? Well, quite a bit on the review, but it's okay. I mean, I think it's worthwhile just to remind ourselves what we talked about yesterday. Are there any questions about this?
Any of you have any questions? Yeah, maybe we can proceed, Henrik.
Good. So people are probably still, it's only 10 o'clock, right? And so people are still sleepy, but it's all right. Today we will be talking about phenomena which happen above the threshold. So yesterday we spent the time on the thresholds for weak sounds, and we were talking about experiments which reveal the properties of the hearing system, wherein you are asking your experimental subjects, can you hear something or don't you hear anything? But of course, most of the listening happens at the levels when we hear something, right? So it's an interesting thing to start talking about two things. And we will be talking about, first we're talking about two things, about the loudness and about the pitch. And I noticed yesterday, as I was listening to Professor Ignanare and the questions, and somebody was asking, there was quite a bit of discussion about why do we use decibels in describing how strong the sound is and stuff like that. This will hopefully become a little bit more clear after today's first hour of the lectures, because the loudness, as we will see, is not increasing linearly with the intensity of the sound, but differently. So what we have in the physical side of the signals, this is what we can measure. We have a frequency, we have an intensity, we have the length of the signal, and we have a phase of the signal. If we are looking into frequency domain, and the frequency, intensities, and the lengths have a certain correlates in the perceptual domain, especially frequency and intensity has been studied since 19th century quite extensively, because the psychophysicists were or still are very interested in how the outside world is reflected inside. what is the effect of the outside sounds on your inside perception. And so they are correlates, at least of frequency and intensity are psychophysical correlates. With frequency, there is a pitch, we call it, so how high the tone is being perceived as we change the frequency. And in intensity, there is a loudness. There should be probably double S there. Sorry for that. A loudness is related to the intensity of the sound. Clearly, the higher the intensity, higher the amplitude, more power you are pumping into the ear, louder it sounds. But how much louder? That's interesting. So here we have the little picture, which is a physical world, is on one side, intensities, frequencies. On the other side, inside your perceptual system, you have a loudness and you have a pitch. And we are interested in what is the function of the outside the world inside. This is what is called the psychometric function. And as I said, it's been studied since a long time ago. The big strides into the knowledge were achieved already in the 19th century. So we know what is the sound intensity. We can measure that with, we look at what is the amplitude, right? So oscilloscope, and now we can see it on our computer screen. But how loud is the sound? We have to ask people. And we have to ask in sophisticated way in order to get this function. So we are after this function. What is the relation between perceived stimulus and to the stimulus which we are putting in? In the frequency, the same thing. You change the frequency, and you have to be asking people how high it sounds. And again, we will discover interesting things. So we have to, in that case, since we are dealing with the phenomena which are above the threshold, so a threshold phenomena, there you are discriminating between hearing nothing and hearing something. In a discriminative experiments, we are asking difference between two things. These differences are also following the sigmoid curve, obviously. Because if the things are very similar, most of the people are reporting there is no difference, right? So basically, most of the people are saying, I don't hear anything. If the things are very different, most of the people are telling you, sure, these two things are different. But somewhere in between, there is a point which we call the just noticeable difference, or in Europe, they call it difference Lyman. But we Americans, we call it just noticeable difference. And typically it's being decided that when 50% of the population is hearing something and 50% of the population hears nothing, we vote democratically and we say, well, this is just in the balance. Like when a political system in the US, there is Republicans and Democrats are always almost in the balance. Half of the population likes Democratic Party, half of the population likes the Republican Party. So this is the point. And typically what we do is that we look at the 75% people telling us yes, and 25% telling us yes, or 75% telling us no, and we take a straight line approximation between the two, because this is the two just noticeable differences. So right there is just noticeable difference. Okay, so now we can start working. Imagine that you sort of play the stimulus, and the first step, which is you discriminating between something and nothing. This is something which we talked about last time. Is there a signal or isn't there a signal? So this is just noticeable difference is the threshold, right? Here we hear nothing. If for this amount of intensity we hear nothing, and if we change the intensity, we start hearing it. So this is just noticeable difference at the threshold of hearing, discriminating between hearing nothing and hearing something. Imagine that this is the intensity, right? So we are cranking up when there is a signal, we can see it on the oscilloscope, but people report they don't hear anything. It is below the threshold, but at a certain point, the threshold intensity increases so that you start hearing. First noticeable difference. Then you can start asking between what you heard before and what you hear next time. And you're asking can you hear the difference between this sound and this sound? So you get second just noticeable difference. You can imagine that you can keep stacking these just noticeable differences one above another. So you do another measurement and you ask, well, I already know what is this level. I have two just noticeable differences here. And you put another one here. And what you discover, that's what people discovered. The Harvard, I mean, the Fechner and Weber actually was the first one, German psychophysicist, that these just noticeable differences are increasing in the level of physical stimulus. So intensity is increasing for the same interval inside your body, because these intervals, you can imagine, they are the same. They are just like just noticeable differences inside your body, and they are related to the internal noise. Because within the just noticeable difference, basically you cannot tell the difference because this internal noise is overwriting what's happening outside, right? So each of these just noticeable differences are reflecting amount of internal noise at given intensity. So it seems like the internal noise is increasing with the intensity of the sound. And if you now we see the points, and these points, of course, are interesting because these points, when we stack the same amount of just noticeable differences and a function of stimulus, what we are getting is what people are interested in, which is a psychometric function, which relates sensation inside the body to the physical stimulus outside the body, and you can put the curve. And if you are engineers, you can of course approximate it. That's what the Weber did, and actually Fechner did it. Fechner was a kind of groupie of Weber, and Fechner discovered this law. We call it Fechner-Weber law to honor his friend Weber. And it says that the stimulus inside the body is related to the logarithm of the intensity relative to the threshold intensity. And there is some constant. And this logarithm here is telling you why people are using decibels. Because actually, if you start using decibels to measure intensity of the sound, essentially you are saying, I believe that Fechner-Weber law is valid. At least Fechner-Weber law in intensity is valid. Because if I plot something in decibels, if I plot intensity of maybe magnitude spectrum on logarithmic scale, or on logarithmic scale, so that I'm plotting logarithmic magnitude spectrum of the sound, I'm respecting what the Fechner-Weber law is telling us. So I hope that this somehow explains a little bit what people were asking yesterday to Professor Narayana. Why is it that we are using the decibels? Because the Fechner told us that a relation between intensity of the sound and perceived loudness is logarithmic. Similar thing has been observed for brightness of lights. But they will see that there is a number of other phenomena which do not follow Fechner's Weber law at all. And we will also see that the Fechner-Weber law is only valid for reasonable intensities. There is typically what's happening is this, what they call it near miss of Fechner-Weber law at low intensities and very often at the high intensities. And we will also see that the near miss is actually quite substantial. But for the reasonable range of the stimulus, at least of sound stimulus, when it goes to the loudness, this Weber law is approximately followed. And sure, soon I will show you that this is not the only function which people are using. And anyways, but Weber law comes from the 19th century and is very much accepted. So here we have it. So you see that if you plot things on an logarithmic scale, now if you plot the relation between the just noticeable difference and the intensity of the sound, so these just noticeable differences are increasing with the intensity, so that the ratio is approximately constant. This is called the Weber fraction. And if we plot it here, it's a straight line. And it implies then that if we plot the logarithm, the intensity on logarithmic scale over the large range of the intensities, this fraction, the Weber fraction, remains approximately constant. So this is telling you what we are perceiving is a relative to something. So we are, when it comes to evaluating differences, these differences have to be measured relatively to the level on which we are evaluating. I mean, it's pretty straightforward, right? And you can also see at low intensities, the fraction is increasing, and at high intensities, fraction is increasing. So this Weber law is approximately constant over the reasonable range of the stimulus between about 10, 15 dB up to about 70, 80 dB decibels. And if they are if the intensities are lower or higher, people discovered that maybe Weber wasn't exactly correct. So of course, just like when we talk about physiology, and I told you that von Bekeschi got the Nobel Prize for the wrong results. People very quickly corrected him, but still he got the Nobel Prize because there was something interesting which he discovered. The same thing, that Weber was only approximately correct, and eventually people start, of course, correcting him, but still the Weber's law, it's still called Weber's law because it was important. For the first time, people got convinced that he could discover the psychometric function between the intensity of the sound and perceived loudness of the sound. Same way, like when Isaac Newton discovered the gravitation law, eventually Albert Einstein and people in 20th century corrected him, because it's always, science always happens. It's relative, right? Knowledge in the science. It's always relates. It's never totally accurate. Somebody will always come with a better speech recognizer than we are building today. Okay. This is for white noise. The Weber's law is mainly missing at the low intensities. I said 20 decibels, but you can see the really straight starts to be, the Weber fraction starts being constant from only about 40 decibels. And but for white noise, it's all the way up to 90 decibels. Just noticeable difference is about the half decibel over the whole range of the intensities. So that actually tells you why it is convenient to display things in logarithmic scale, because more or less what we are seeing is what is it that we are perceiving. And just noticeable difference in intensity is about 1 decibel over the reasonable range for white noise. When it comes to the sounds which are not noise, things are a little bit different. We'll see that they also depend to some extent on the frequency. So we know this. We came up with stacking just noticeable differences, and we came up with Fechner-Weber law. I forgot to tell you that in 20th century, the group at Harvard, with Professor S.S. Stevens, came with a difference, because he said, well, you know, that was all 19th century. Now it's the 20th century. I will show you that maybe this the psychophysical function is not quite logarithmic, and as a matter of fact, it cannot be logarithmic because they are stimuli, which is logarithm is compressive function, right? Larger the intensities, the more the world inside is compressed. But there is some stimuli. I think I have a slide for that, or if not, I will tell you that this is not true at all. So S.S. Stevens came up with another technique which wasn't stacking, just noticeable differences. So wasn't stacking these intervals of the where the internal noise is being overwriting the signal, but he was directly asking people how loud the sound is. How strong is the stimulus? And when he started doing it, people say, well, this is a nonsense. You know, you just can't ask people how loud something is. Turn out that you can. Because what he was doing, he said, I will play you one sound, which is like, you know, like your standard, and then I play you another sound, and you just give me a number. Does it sound twice as loud, or does it sound half as loud, and that sort of thing. And did it many times, and discovered that the relation between the outside world and inside world is more like a power. Well, of course, the powers which are less than one are also compressive. So he discovered that for stimuli like loudness, relation between loudness and intensity is intensity put in taking an intensity cubic root of the intensity. Intensity on a power 0.33. If you plot a logarithm and a cubic root for the numbers, of course, larger than one, when the logarithm is compressive, you will see that this is not all that different. But he said this advantage of this way of deriving a psychometric function is that it's true over the wild range of the stimuli. I don't have we talk about the sounds here only. So for sound, cubic root, the relation is through the cubic root. Same thing is for brightness, but there are stimuli such as electric shock, where the power is larger than one. As a matter of fact, electric shock, if I remember it well, is about 2.5. So stronger shock is more, it's shocking, right? Taste of the coffee is also saltiness. If you are putting twice as much salt into your food, it tastes more than twice salty. So there's a number of stimuli in this world where this exponent is larger than one. But for loudness and brightness, it's for both of these stimuli, it happens to be cubic root or close to cubic root, right? So this is something which we are using quite a lot. When I will be talking about some of the auditory processing techniques. It turns out that taking a power spectrum and putting it into cubic root, you may get some advantages, because you are essentially what you are getting into. You are getting into loudness domain. So it's telling you that in order to make the sound twice as loud, you have to increase the intensity about 8 times. So in order to make your stereo sound twice as loud, you have to invest into amplifier, which gives you about 8 times more power. So if your friend has an amplifier which puts out 1 watt, in order to make your music twice as loud, you have to have amplifier of 8 watts. And if you have already an amplifier of 8 watts, you have to get an amplifier which gives you 64 watts. And so it's an interesting thing. You have to see that things are still compressive in your perceptual system, and according to S.S. Stevens, the relation is a cubic root. Okay. Now, so we are above the threshold, and we talk about the thresholds of hearing. And here we have the curve, which was the first curve which I was showing you yesterday. This is a threshold curve. But now we can also start measuring how the loudness of the sound is changing as we are changing the intensity of the sound on the at different levels and as a function of frequency. And what we can see is even we see the severe differences, nonlinearity at the threshold, but for the normal sounds, it's still the difference, but the difference between low frequencies and mid frequencies is a little bit less. While here the difference is about 60 decibels between 1 kilohertz and 30 hertz, here the difference is only about the 20, only about 40 decibels. And here the difference is only about the 10 decibels at 80 decibel range. So the things are getting flatter and flatter. Each of these curves, they are called equal loudness curve. And what they are telling you, how to keep the loudness of the sound equal at certain number of phones. This is measured in phones. As you change the frequency, when you go to the lower frequencies, you have to keep increasing intensity for the sound to sound the same of the same loudness. Why is this important? It is important if you are maybe building a hi-fi system, because if you're building a hi-fi system and you have to, and you're selling it to somebody who will use it at your college dorm, you cannot play the sound of the symphony at the level of orchestra in a symphony hall. You have to compensate for these differences, because if you didn't compensate a frequency response of your amplifier, your sound would sound totally flat. You wouldn't like it. So people who are building hi-fi systems, they know it. And as you turn down the volume, you are automatically boosting up the low frequencies and high frequencies, called the physiological loudness control. And it's again, it's being used since the mid of the last century. But this is, of course, you can imagine that to derive these curves was quite labor intensive. You had to ask many people for many sounds, at many intensities and many frequencies, and so that could be done only in the places like a Bell Labs, where it happened for the first time. Fletcher-Munson curves they are called. Professor Dr. Fletcher and his colleague Munson, they were working on it for a number of years, and then they got it. Now, the interesting sort of piece of trivia is that if you do this, if you measure these equal loudness curves nowadays, they look slightly different, because people hear a little bit worse in average, because we are exposed to many more sounds. Interesting thing. Maybe also they are slightly different because people do more careful measurements, but for us, this is what it is. We know that we don't hear very well at low frequencies, not only at the threshold, but also at the reasonable levels. Speech happens here between the 3 kilohertz and about, this is a telephone speech, 300 hertz and 3.5 kilohertz over the intensities between 40 and 60 decibels. Around the loudness curve for about 40 decibels. But even at the loudness curve, 40 phones, even if you say, because phones and decibels are equal at the 1 kilohertz. So this 40 decibels is the intensity of the sound, and perceived level at 1 kilohertz is 40 phones. So typically what we are doing here is that if you want to emulate this property into your system, maybe you want to pick up this curve, because it's a kind of a reasonable average curve to be valid over the range of the speech signals. And that's what when we talk about the techniques, that's what I remind you, that's what we do. Good. Of course, my favorite thing, as you will discover next hour, is time. So it's interesting thing is how the loudness is increasing with the duration, and how the loudness is increasing with the duration. For the short durations, the loudness is decreasing for the same intensity. So just like at the threshold level, when I was showing you when the signals are very short, you have to, the threshold is is higher. You have to make the signal stronger. Even for the loudness, if the signals are shorter than about 200 milliseconds, intensity has to be larger for the loudness to stay the same. So here we have the duration. Here we have the required intensity for for the given loudness. And we can see that the loudness is a function, strictly function only of intensity for the stimuli which are longer than about 200 milliseconds. If the things are shorter than 200 milliseconds, we have to remember that the relation is different, that intensity has to increase for the loudness to stay the same as the signal. Again, I mean, this is a quite convincing argument for existence of some hypothetical buffer in your hearing of about 200 milliseconds about the syllable length for speech people, which needs to be filled up first before things become a little bit stable. If the signal is shorter, you have to make it stronger so that energy of the stimulus remains approximately the same in order for the loudness to stay the same. Similarly, just noticeable differences in frequency are, of course, functions of the frequency of the tone, but this Weber's law here, you can see it's valid only from about 500 hertz up. For the frequencies lower than 500 hertz, there is a big deviation from the Weber's law. Here is the Weber fraction, which is a delta F, just noticeable difference in the frequency over the frequency itself, and you can see how dramatically this Weber fraction changes for the low frequencies. And also, the Weber fraction is to some extent sensitive to intensity of the sound. If the intensities are larger, the Weber fraction is less. So you know that, as I said, I mean, 20th century came and everybody spent the time to show how wrong the Weber was. But still, we learn a lot about the thing. An interesting cut is actually this around 500-600 hertz, because we'll see from about 500-600 hertz, critical bands start to increase up to about 500-600 hertz. According to some measurements, like German measurements, they seem to be the same. So a number of things are happening at the cutoff frequency around 500-600 hertz. When we talk about the Merle scale, we'll see very similar perception of pitch, which we'll talk about shortly. We'll see very similar thing. So this is what we have here. Just noticeable difference is constant, not the Weber fraction is constant up to 500-600 hertz, and then it starts increasing so that here the logarithmic relations starts taking over. So Weber law is taking over. But what we are seeing here is something which the reason why I have this slide here, so it's very clearly we see how sensitive we are to changes in the frequency. So if you are asking people, giving them two tones and say, do they have this, do they sound, they are the same in frequency or not? If you change by 1 hertz, people are already reporting, I hear something different. So this is a little bit of puzzle, right? We have these critical bands, which we sort of said, well, critical bands are the filters which are implying frequency resolution of human hearing, And now you are telling me that I can tell the differences of 1 hertz, while the critical bands are at least 100 hertz. Something must be wrong. Are you making it up or what? Well, no, because what critical bands are telling us about the resolution of human hearing. They are telling us how well you can resolve different components. They are not telling you how sensitive you are in the frequency composition of the signal within the critical band. And what really, when you are looking at these high sensitivities of hearing to very small differences in the frequency, some people say, well, clearly it is. These are the critical bands. This is a just noticeable difference in the frequency. Well, the relation is about 2 orders of magnitude almost difference, right? So something must be, we have to explain that. We have to know why. Remember the question why. Some people say, well, of course, I mean, we have to remember that these critical bands are highly asymmetric, and high slope of the critical band shapes is very, very sharp. As a matter of fact, some people say it's about 100 decibels per octave. You know, it's very, very sharp. The critical band filters are very sharp towards the high frequencies. So if you think about it as an engineer, you realize if you have 2 components which differ about 1-2 hertz, and they are projected on this slope of the critical band shape on the higher level slope, the difference in intensities at this point is huge. This is what we are perceiving. And you know, I don't have to explain you, these critical bands are totally hypothetical things. They can be created around every frequency of the spectrum. There is infinite number of, well, very large number of critical bands over the range of your hearing. But when we are modeling it, typically we put 1 critical band per one bark. But this is what's happening. So So when you are evaluating the differences in the frequencies, it might be, we don't know, but it might be that we are using this sharp cutoff frequency, cutoff slope of the higher slope of the critical band to evaluate the differences in intensities. And also, of course, there is also rate theory of hearing. You remember that? I mean, which has nothing to do with the critical bands. It just tells you up to 5 kilohertz, our brain has spikes coming from the ear, which are in synchrony with the frequency components of the sound. So it's probably we can actually tell the differences, very small differences in when the spikes are changing the spacing of 1 hertz. That's what brain may be able to do. So we don't know. There are 2 theories as far as I know. One goes back to rate theory to get away from the shape of the critical bands, wide width of the critical bands, and say this is not being used. The other one is, well, you can even stay with the place theory, as long as you accept that these shapes of the critical band filters are highly asymmetric, and towards the high frequencies they are very sharp. Okay. I may be running a little bit over time in this case because, you know, I want to certainly discuss this part because this is interesting. This is related to the MEL scale because most of us are using MEL filter banks now. Why are we using MEL filter banks? Because it's related to the perception of how the different frequencies are being perceived by our system. How high is the tone? If I give you a tone of 200 hertz, and I give you a tone of 400 hertz, and so I can ask you, how high are these tones? So how much higher and how much lower is one tone than another? If I give you 1 kilohertz, I can ask you, can you set up another tone? I give you the control over the frequency so that it sounds to you as twice as high. That's what happened in 30s of the last century, Bell Labs. And people were asking, say, can you do that? And they were running these experiments a number of times. Very quickly, they discovered in order to get a tone of 1 kilohertz sounding twice as high, they have to put the frequency not at 2 kilohertz, but at 3.5 kilohertz. So clearly there is going to be a large nonlinearity between perception between what we are perceived as how high the tone is and what is the frequency of the tone. And after a while, they came with a curve which is called the Mel curve. Interesting thing is this Mel curve. Actually, they approximated it very quickly, but this is S.S. Stevens from Harvard, but these people are, the experiments were done in Bell Labs, as far as I know. So after a while, they quickly approximated it by the function. And the function is that approximately linear up to 700 Hz, cutoff point is 700, right? And from 700 Hz is becoming approximately logarithmic. So this is the function, and this is what we are putting into this frequency speech analysis or auditory analysis. It has nothing to do with the resolution of human hearing and nothing like that. It has to do something with the perception of pitch. But the reason why it works is that the difference between critical band and the pitch and Mel scale is not all that huge. Essentially, both of them are compressive towards higher frequencies. Both of them are approximately linear. Here, it's linear up to 700 Hz. Here it is linear to 600 Hz. Here we are using, there's a number of approximations to critical band shape, right? But sine is hyperbolic here. It's approximately similar to logarithm here. Both of the curves are becoming logarithmic from about around 600 to 700 Hz. So this is the reason why we are using Mel spectrum. Some people use the Bark spectrum. Bark scale is a critical band scale. Mel scale is a scale which reflects the perception of pitch. Good to remember, but as I said, since we are engineers, we don't really care all that much about the small differences, and they both work okay. So it's fine to use Mel scale. The only thing which is maybe not fine when we get into Mel frequency analysis is that people now are using more and more filter banks. And as they are being derived by most of the software packages, they are getting narrower and narrower. So I don't know if this is correct, but anyways. So pitch is perceived as a periodicity, right? I mean, I hope that it's just set up that you can hear something, computer sound. You hear the melody?
Yes, able to hear.
Good. So this was the pure tone, right? I mean, oops, sorry.
It's a single tone, correct?
I can play the same melody through the more complex tones. Those of you who know Fourier analysis, which I believe most of you do, is that I just provided higher harmonics. Periodicity is the same, except that the shapes are very, very different. They sound different, but I hear the same. Okay, of course, I know why, because you are having this fundamental frequency and the higher harmonics. Well, what happened if I filter out the fundamental frequency? I can filter out everything what is lower than 1 kilohertz. That's very puzzling, because suddenly I don't have the fundamental frequency at all, which was playing melody here. And I can still hear the same melody. So why is that? Of course, I don't need to have the fundamental frequency there in order to perceive the periodicity of the signal. I can filter it out, and people in the California knew it very quickly because the Bell Labs people were very much into making money. So they discovered that they don't have to give the frequencies below 300 hertz to listeners, and still people are happy to use the telephone. Even when the fundamental frequency of the voice, male voice is definitely much lower, and even female voices, typically they are much lower than 300 hertz. You can filter it out and still people are perceiving okay. And even they perceive the melodies, except they sound really. So phenomenon of missing fundamental was studied quite heavily and seriously.
Pitch of the missing fundamental, or virtual pitch. You will hear a complex tone with 10 harmonics. First complete, and then with the lower harmonics successively removed. Does the pitch of the complex change? The demonstration is repeated once.
So 5 harmonics were removed, and you can still hear the same pitch, right? I hope. And pitch is 200 hertz because fundamental is 200 hertz. And even when you remove the 5 lowest harmonics, here your hearing looks at 1200 hertz, 1400 hertz, 1600 hertz, 1800 hertz, and so on, and says, well, pitch has to be 200 hertz because this is a common denominator. Well, that we already knew, but what happens if, so I play this, right? If I play this, but then I can artificially shift all the high harmonics by 50 hertz. What happens?
Now you hear a three-tone complex of 800, 1000, and 1200 hertz, followed by a complex of 850, 1050, and 1250 hertz. As you can hear, their virtual pitches are well matched by the regular harmonic tones with fundamentals of 200 and 210 hertz. The sequence is repeated once.
So the second one is the matching tone. That's what people are asked. So you play them this complex tone of harmonics of 200 hertz. And this is a natural harmonics. I mean, they are really okay. People, of course, fitted with the sinusoid of 200 hertz. But when you shift everything up, people pick up on this middle harmonic here. And they don't care so much that the lower harmonic, this is a, how is it? This is a fourth harmonic, this is a sixth harmonic. Fourth harmonic and sixth harmonics are mistuned. They pick up on this harmonic and they report, they match it with the 210 hertz. So it's telling you the things don't have to be exactly like in engineering, in psychophysics. Hearing is picking up the most reasonable estimate, but people are still capable of matching these tones. And of course, I can show you even more experiments in this respect because there is more. Where sometimes you would start seeing bimodal or even trimodal responses if you do the statistics, because some people are picking up on the middle harmonic, some people are picking up on this one, some people are picking on that one, but they can still match even the tones which are totally unnatural because they are not natural harmonic tones, right? They are created by computer. Okay. Basic pitch and duration, I think we are getting slowly to where I want to be, which is like sort of for the lower durations up to about 200 milliseconds. There is a big range of the people can't match the pitches very accurately. Typically, they are underestimating. So means for the shorter durations are getting lower than they would be when the signals were longer than 200 milliseconds. But also the range, the variability of the responses is larger. So again, the reason I'm showing it is because next hour we'll be talking about the timings, and the timing seems to be such that up to 200, when we look in the time domain, below 200 milliseconds, people cannot do things very accurately. Only after signals are longer than about 200 milliseconds, after this mysterious syllable length buffer of the human hearing gets filled up, things become more stable. Okay, I think that's about it, what I wanted to talk about. I also wanted to tell you then that the Mel scale and musical scales are related. Mel scale is logarithmic from about 700 hertz up. Musical scales are logarithmic, you know that. Yes, the octave is twice as high, and no matter at which frequency it happens. But the fact is that since the percept of the pitch is only approximately logarithmic, only for the higher frequencies, when you change the scale, those of you who are musicians, you may know that if you play something in a C key and you change it suddenly into a different key, the B key or something, suddenly the music starts sounding differently. The sensitive people actually know that if something is written in the C key, it should be played in C key, and you shouldn't be shifting it into different keys, because suddenly the music intervals start sound differently. I have several slides on this topic, but maybe let's not worry about that. Let's take 5 minutes. I will drink a little bit, and in 5 minutes we'll dive into the next part, which is going to be more into perception of sequences. Because sequences is what we are listening for. So far, we were playing the steady tones and simple tones. It's not all that interesting, right? I mean, the real stuff starts happening when we are playing with a more reasonable sound. So we spent at least an hour on more reasonable sounds. 5 minutes, Rosanna, okay?
Yes, sir. It's fine. I can go.
Okay. In 5 minutes, I'll see you. Yeah.
Yeah. So, yes, sir. Yes. 11:15 we can join. 10 we can join.
Yeah. Okay. Are we ready to go?
Yes, sir. Probably we can take some question from previous part.
Sure. No problem.
Participants want to ask, then we can proceed
Yeah.
for. Yeah. Anybody want to ask any question?
Excuse me. Yeah. Hello, sir. Uh, Sir, these psychoacoustic phenomena as well as loudness curve, so they've been studied in detail with reference to a large set of audio signals in a sense. So, is there any specific studies that have gone to speech sounds with reference to these psychoacoustic phenomena, and why do they sound the way they sound? I mean, has somebody experimented on it?
What was the word? Are you asking about the speech or what is it?
Sir, be it like critical bands and loudness phenomena. So they have been extensively studied with reference to audio signal in
I
general.
see.
Yeah, in
Uh-huh.
general. So are there any studies specific to speech sounds with reference to these phenomena that somebody has studied and reported that you are aware of? Yeah.
I hope to be spending at least 1 hour on some studies where people were using speech and it's related to the critical bands. It will take about an hour. So the answer is yes. Of course, people do. I mean, psychophysics is being studied for speech too. I mean, clearly. Of course, the classical psychophysics uses pure sounds because it's cleaner. But what we already be mentioning today is it's more related to the more realistic sounds which are being changed at least in time. But when it comes to speech, yes, there are some psychophysical studies in speech. I won't be mentioning all that many of them, but at least one I will be talking about towards the end of this course.
Okay. Yeah. Thank you, sir. Thank you.
And it's a good point. What you're pointing out is actually it's also often criticism of the classical psychophysics as related to normal world, because in normal world we are not listening to sinusoids, right? And we are not listening for steady sounds. And actually it's already slide which is now on, it's already related, it's slightly talking about that, but because the world is changing, at least we are perceiving sequences of sounds, and we are perceiving sounds which are more rich, and speech is one of the sounds which is of course very important. So yeah, we will spend at least an hour on perception of speech.
Yeah. Thank you, sir. Thank you.
Sir, one question in the chat box that
Uh-huh.
is it the interval difference in notes of musical scale, say major and minor, which gives them their distinct sound and feels?
I mentioned it maybe a little bit towards the end. Musical scales are logarithmic, right? It's and they are equal intervals on logarithmic scale. When it comes to octave or fifth or third, all these intervals are relative, and so they are expressed on logarithmic scales. In terms of perception of the pitch, we observed that things are approximately logarithmic only for higher frequencies, about 1 kilohertz. Actually, cutoff frequency is in case of pitch is 700 hertz. So I mentioned that changing the key, playing music in different key, changes the percept of the changes the mood of the music. So, but the reason why we are using just the same way why we are using decibels for intensities, we are using the musical scales and logarithm is because perception is approximately logarithmic. I don't know if I'm answering that.
Kumar, is that your question is answered? Yeah, got it.
You can ask more.
Yeah.
I don't know if I will have all the
Others
answers.
want to ask any question? Okay.
Okay.
Yeah, fine.
So this part is maybe getting slightly closer to the real world. We are not going to be playing anymore with the steady sounds, but we'll be talking about the sounds which are at least changing in the frequency. And so introductory slide I have here, the part of the from the Lewis Carroll, Alice in the Looking Glass, who says, well, you know, things are changing in the world. If you want to, if anything should carry any information, that needs to change, because if I think Professor Eglander already mentioned that if somebody is saying all the time, it doesn't really carry much of the information. You have to change the things in order to create the information. Here we have a speech, and we can see the speech is a sequence of different sounds. Here we have a music, and we see that music is a sequence of changing sounds. So information is in time frequency plane, right? You know that here is separating different frequency components of the signal into different frequency channels. So the frequency is to some extent, and it's important. But what is even more important is that things are changing in time. So let's talk about time. First question is, how sensitive are we in changes in time? You can do the experiment. One of the classical experiment, again, is the experiment with the clicks. You play 2 clicks, which have the same magnitude spectrum, but they have a different phase spectrum, right? Because this one has, this sequence has an opposite phase spectrum than this one. And you ask people, can you hear the difference? So you have to so that you need to rely on a percept of the difference in the timing, and you discover that people start hearing differences of the order of 2 to 3 milliseconds. And so if delta t is 2 to 3 milliseconds, people refer the sequence A is different from sequence B. But that's telling you something about absolute sensitivity to differences in timing. What is even more interesting for us is that what is the time constant of the human hearing? What is the sluggishness of the human hearing? And just like what we were talking about, the percept of the differences in frequencies, which is very small, you can hear the differences of the order of several hertz. But the critical bands are at least 100 hertz and getting broader and broader towards higher frequencies. Here we hear the differences of the order of 2 to 3 milliseconds, but we will see that sluggishness, temporal resolution of human hearing is much, much less than 2 to 3 milliseconds. This is a sensitivity to differences. It's not telling you much about the temporal resolution of human hearing. For the measuring the temporal resolution of human hearing, my favorite experiment was this. You ask people to perceive the differences, the gaps in a white noise. You play the noise, you put a gap, and you play the noise, and you ask how long this gap needs to be in order to be perceived as a gap. Well, of course, I mean, if the noises are of the same amplitude, the difference is very small, 1 to 3 milliseconds. But it's not telling us much about what the temporal resolution of hearing is, what the sluggishness of hearing is. How do we perceive this gap? We perceive this gap because there is a memory of the first part of the noise, which is decaying, and we want to estimate this time constant of the decay. So from this experiment, we know that if the following sound is the same intensity as long as this, as a difference between the coming sound and the memory of the previous sound is equal to just noticeable difference in loudness, people perceive it as a gap. Because people perceive the gap because there is a difference between what's now and what they remember from before. But how to estimate this time, the time constant, we have to run a series of experiments which are a little bit different. So we have to change the second amplitude of the tone and then follow how the perception of the gap is changing. Because if what we will discover very quickly, if the second part of if the noise after the gap is lower in intensity, then the gap perceived gap, now gap starts being perceived as a gap only for much longer intervals. So you can do this experiment. So eventually, it will memory of this first part of the noise will decay to zero. This is what, and we are interested. How long does it take when it decays to something which is zero? So we run the experiment, and we change the intensity of the second tone. Here we have the values of the second tone, second segment of noise, and we can see that percept of gap is changing for when the first tone was 65 decibels, and second segment of noise was 10 decibels. The gap was perceived only after the delay of 100 milliseconds, because it's basically because the gap is being perceived only when the memory of this previous band of noise decayed. So, and you can run it for other intensities. You can change the first intensity, and you start seeing the very interesting thing. The memory of the gap is also decaying, but it's decaying with different rate. It's very similar to something what we have seen in the perception of in temporal masking, and you can look where this whole thing would end up if you kind of make these things straight approximations. It will end up somewhere about a couple of 100 milliseconds. So it's suggesting, this experiment is suggesting in a very different way a phenomenon which we have already seen in the perception of the temporal masking, which is like memory of the previous tone lasts for about 200 milliseconds. So the time constant of human hearing, sluggishness of human hearing, is of the order of several hundred milliseconds. This is well known to musicians. If you play the sequence of sounds, and these are those of you who are musicians, you know that this tone should be twice as long as this note. This is a half note, this is a quarter note. So this is what an artist wants to create in the ear of the listeners. The good musicians know that in order to create such a sequence of the tones where these ones are half long than this one, they have to make these tones much shorter, because what is really being perceived is this tone through the sluggishness of the human hearing. And so what really matters is how long these intervals are, right? So physical length of tones is different than perceived length of tones. So there seems to be sluggishness, and the sluggishness is being used to some advantage. This is an experiment which has been done also a long time ago, in the middle of the last century. What you discover if you play the sequence of the sounds, I wish I had examples here, but I don't. But if you have a sequence of sounds, these are the sinusoids of the certain length, but the differences are small. You hear this as a sort of gallop, something like that. If the differences start in frequencies are starting to be large, suddenly you discover that you are perceiving two streams of the tones. Because what happens through the sluggishness here, through the sluggishness of hearing, they merge the tones of frequencies which are close in frequency, they merge through the critical band phenomenon into one stream. While here the frequencies are large, so these tones fall into one critical band, these tones fall into another critical band, and sluggishness creates the percept of the continuous two sequences of tones. Experiments has been done how these two things are related. If the pulse durations are short, about 50 milliseconds, for the frequency differences up to about 20% is still being the things are still being perceived as one stream. As the signals are getting longer and longer, the frequency differences between two streams can be tolerated much more much less in order to be perceived as the two streams. Here is the region where the percept is ambiguous. Some people are reporting one stream, some people are reporting two streams. But in order to hear two streams for the longer time segments, the frequencies between these two streams can be much larger, because basically this integration, this experiment, if you start thinking about it, is telling us a lot about integrating things in time and integrating things in frequency. And these two things are related, so the whole integration is happening in a time frequency plane. And so these experiments are very interesting. There's been a whole PhD thesis on that topic by Van Norton, 75, about this fusing things in time frequency planes. And it points into the importance of the critical bands, and it points to the importance of the critical time intervals in a very predictable way. If you play sequences of harmonic tones, this is the fundamental, and these are harmonics. Here you see that in first experiment, here we play the fundamental, and then we play the harmonics of the fundamental, and in the periods between the fundamental. This thing is being perceived as two streams. Why is that? Because this fundamental tone is being integrated into one stream, while these things is being integrated into two streams. I mean, another stream. So people hear two streams of sounds. Why is that important? Because it's already telling you something about the ability of human hearing. I don't know if one should call it attention, but certainly one should call it into ability of separating rich sounds, richer time frequency sounds in time and frequency into different streams of information. So here we are hearing two streams because differences in timing is sufficient and differences in frequencies are sufficient. Even if you leave out the fundamental, this is going to be perceived as a single stream, while the tones which are put into in the gaps, they are in higher frequency. Another frequency is perceived as different stream. While if you move these harmonic tones closer, and those are the harmonics of one fundamental, and these are harmonies of another fundamental. This is going to be perceived as a single stream. Why? Because the differences in timing are sufficient, and differences in frequency are small. So again, I mean, there's a number of experiments like that. I picked up two, which I saw that they sort of look a little bit clear. But what I wanted to show here is that our hearing is capable of integrating different components in frequencies and different components in time into the information streams. These information streams can be one or can be two. And so imagine that it may be the one can be speech of one person and one can be speech of another person. And the reason why we can separate the simultaneous speech of two speakers is because we can form one speech of one speaker into one stream and speech of another speaker of another stream, and selectively we can pay attention to one or another. Those of you who are listening to music, you know that you can quite easily focus on the melody played by individual instruments in the assembly of instruments, because each music is written in such a way that very often one instrument is playing one melody and another instrument is playing another melody, or even the single instrument, a good pianist plays or a good composer can create the music so that it streams into different information streams. And human hearing is excellent in picking up different information streams. So these things were studied heavily. There is a whole book by Bregman, if you Canadian professor, who is book is pretty thick, which talks all about the streaming and all about creating the streams of information by human hearing. And the people who study, somebody was asking, you were asking about the perception of speech. Of course, I mean, we know there's one of the significant and important phenomena is the cocktail party effect. In cocktail party effect, we observed that you can follow the speech of single person in a mix of the speeches of other people, because we are creating the streams of information in our head and can selectively pick up one line or another line. Talking about the timing, I mean, if you play two tones and you are asking which tone starts first, if the difference in the tones is less than a couple of 100 milliseconds, you may not be able to tell. You know that you hear the two tones, you know that they are starting at different times, but you don't know if the tone 1 started before tone 2 or tone 2 started before tone 1. 200 milliseconds here, if I have seen one. If you play the sequences of sounds, you have two different sounds. And in order for you to be able to tell what is the temporal order of these sounds, again, the sounds has to be longer than a couple of 100 milliseconds, maybe 300-400 milliseconds. Before that, you cannot tell the difference. So it's telling you a lot about the ability of human hearing to integrate things in the time or fusing things in the time. And this is something which we were born with. So this is not something which you can change. And you have to, if you are creating sounds which carry information such as speech or music, you have to count on that. And my point is that just like a good music composer can compose the music so that it can use this ability of human hearing to fuse things into different streams, the same way a speech is being organized in such a way that this fusing of different speech sounds in time through the co-articulatory effect of the speech production is being used to advantage to create the information streams which carry the information which you want. Getting closer to speech, this is an extension of the experiments by Richard Warren, who did a lot of experiments in these timings and this sort of things. So I already told you the order can be recognized only if the different length of the signals is longer than 200 milliseconds. Actually, significantly 100 and 200 milliseconds. From 300, he reports, people start be able to tell the differences. But you can see in these tones, they are very sharp changes. So this tone ends up suddenly and next tone starts. If you change the shape so that it looks more like what you can expect from the speech, suddenly you can recognize the order of these different sequences of sounds much better, even for the shorter segments of sounds. For sounds, oh sorry, this is some bad. Somehow it got corrected by spell checker, I guess. So if you create the segments which change gradually, suddenly you can tell that the order is blue, red, green, blue, or purple. And if you create the sounds, which actually you can create sounds which are shorter than 200 milliseconds, like 1, 2, 3, 4, right? So each of these digits are the syllable, and they are very short. People can recognize the order of the syllabi perfectly, because this is something which, because they look more like this. They are, of course, also richer in the frequencies than just the simple sounds. But if you create the sequence, if you just cut off, even if you cut off centers of the vowels and put them one after another like this, with sudden changes, you cannot tell the difference. You cannot tell the order, because this unnatural change of the abrupt change smears out the whole percept into something which into a big mess. So your hearing cannot tell the order. So it's perception of orders. If you are interested more into something else than just steady tones, and which we spend on 3 hours on already, it's very interesting. As I said, I mean, I would suggest that if you want to study the percept of the sequences, Bregman's book is excellent. What I want to get into is another type of time changes, which actually turns out to be very important for perception of speech, and we will be spending more time on that, which is a perception of modulations. Because the typical sounds are being modulated. They are, I mean, be the music or being the speech. They change in frequency, they change in intensity, and the simplest experiments which you can do if you are a psychophysicist is that you take your sinusoid and you modulate it. Maybe you modulate it using amplitude modulation, and you can modulate it using the frequency modulation. Amplitude modulation changes the amplitude of the sound, frequency changes the frequency of the sound. In both cases, you can ask people, if I change the depth of the modulation, do you hear that sound is a difference between modulated and unmodulated sound, or don't you hear it? Because if the depth of the modulation, if the differences between amplitude here and here is not very large, people don't perceive it as a modulated. People perceive it more as a as a steady sound, right? If you change the frequencies a little bit, again, people don't hear it as the frequency modulated. But if the changes are sufficient, then you start hearing the sound as modulated. And what kind of experiment you can do there? You can ask yourself, if I change the frequency of the modulation, which modulations are perceived the best? And there was an experiment which, to surprise, has been done actually in the first quarter of the last century in the laboratories, because people there very quickly discovered if they are they were studying, the laboratories people were studying a lot of psychophysics, but the goal there always was to understand perception of speech. So even then, but of course, I mean, if you cannot start just playing with the speech, you have to start playing with the simpler sounds in order to get the definite answers what your hearing system is doing. So one of the obvious experiments was modulate the sounds, say take 1 kilohertz sinusoid and modulate it, amplitude modulate it. It was easy way to do in the 1920s of the last century, and change the frequency of the modulation and the depth of the modulation, and ask, when is it that you start, what is the threshold of perception of modulations? And here is the answer from 1923, Rees. People were most sensitive to modulations around 4 hertz. So you see that this is this Weber fraction for the modulations, and you can hear that, you can see that most sensitive, the system is most sensitive to relatively slow modulations. 4 hertz happens to be speed with which we are producing a syllabi in general. So not surprisingly, you have to start thinking, is it possible that we are learning how to produce speech in such a way that it falls, the changes which we need to recognize in the speech signals fall into the point where we are the most sensitive to. This experiment has been repeated a number of times. I cannot help to show you the PhD thesis of Gary Green from 1980. So he collected all kinds of data from the literature and on amplitude modulation, on frequency modulation, and you can see that all of these experiments were pointing that the hearing is most sensitive to relatively slow modulations of the order of 4 hertz. In late 70s, early 80s, people came with the observation that you can measure the modulations of the real speech, natural speech, by doing the following experiment. You take your spectrogram and you sort of pretend that you are doing what your hearing might be doing, which is to separate the frequency components into different frequency channels. So this is a frequency channel at this frequency, and this is the energy fluctuation. This is how the energy in this frequency band is changing as a function of time. Once you have a signal which changes in time, what you can do the spectral analysis of this energy, right? So you remove the mean and you put it, actually what you do is that you differentiate this, what am I doing here? You differentiate this temporal trajectory and you put it through spectral analysis. And what you see here is where the most of the energy in modulations is at a given frequency in time. This came from the PhD thesis of my PhD student, Carlos Avendano, who is now a boss at Apple, working acoustic processing. So that was actually very interesting work. But it repeated more or less what people have already seen in a Dutch group from a group on auditory perception at Eindhoven. And what you also observe is the depth of the modulation Yeah, where the peak is and how deep the peak is related to how good the acoustics of speech is, and they proposed a technique called articulation index, which can be used for evaluating how good the percept of the speech will be in reverberant environments. But this is the most interesting thing. I mean, I've been showing it over and over again, because it seems like that we speak in such a way that we are naturally enhancing the rate where human hearing is most sensitive. So to my great pleasure, I think I have another 10 minutes, my great pleasure, people at Maryland came up with an extensive experiment where they would took a lot of speech databases, they made Switchboard, Bucky, audiobooks, and they would be doing exactly, very similar to what Carlos was doing, that they would be collecting the typical rate of modulations for different types of the databases over a lot of speech. And for sentences, conversations, interviews, audiobooks, where is the mean? Around 4 hertz. As a matter of fact, if you put the mean modulation spectra from these different sentences, they all have a peaks around 4 hertz. It's so accurately on that sometimes I'm joking, because this paper took about 2 or 3 years to get published, because I think the reviewers couldn't believe that you could get something like that. Eventually it got published. Actually, you can read it. It's very nice paper. David Popple was a senior author who is now at NYU. So it is very nice work. They did the same thing for different languages. I said, okay, if we are getting the same picture for different types of speech for American English, what happens if we use the different languages? American English, Mandarin Chinese, French, still the same picture. Everybody speaks the same. If you look at a big population of people, all of the people tend to be speaking in such a way that they are emphasizing the rates of change which the human listeners are most sensitive to. If there is one thing which is very supportive to this notion that speech evolved to fit the properties of hearing, this is a slide I brought on the first hour. Here is the one. People speak so that it can be easily perceived. So falls in terms of the rate of speech, rate of changes, in average, everybody speaks so that it falls into the correct rate of modulations. Can't help to show this. I mean, so this is an old experiment from this is a sensitivity, right, curve. This is the spectrum of speech. This is something which actually I didn't talk much about, but this is also was done in my lab at Hopkins, where we took a lot of receptive fields from the cortex of the ferret, and we, oops, okay, I hope that it starts again. We took a lot of and we computed a temporal component. The idea was we would like to know what is the transfer function of auditory cortex, modulation transfer function of auditory cortex of the ferrets. Where is the peak? Somewhere around 4 hertz. This is something which I may get into or not. This is a very current research. Actually, is being published in Interspeech. So, if you are more interested in, then you may look up the paper by Samik, where you measure the mutual information between speech sounds and modulations of the sounds, and you see where the peak is, very much similar to where the most energy in the modulations are. So people are very good in listening for things which change relatively slowly between 3 and 5, 6 hertz. You can do this experiment. You can play the music and you can ask people, can you estimate what is the rhythm of the music? Just push the Morse code. This was done at I believe, at Munich at Zwicker's laboratory. And so what they did was, what people observed is, this was the histogram of the tapping for different pieces of music, slow music, fast music, all kinds of things. Here we have the histogram. Most of the tapping happened at this 4 hertz, right? This is the modulation spectrum of this pieces of music. This is the sensitivity of hearing to modulations. You can even ask the people to do the same thing for speech sentences. You play them a speech instead of music and say, tell me what is the most typical rhythm of speech which you hear in continuous speech. In about 4 taps per second. Every 250 milliseconds, people hear that this is the speed with which speech is being produced. I don't know how much I should still show you. I think I should be slowly finishing. Maybe I show you this experiment. This is kind of interesting. What you can do is you take the speech and you cut the segments of speech and reverse each of these segments. So this segment is this part of the segment of the continuous speech reverse. This one is a reverse, and you put it together. So every segment of certain length get reversed. So phase of this segment changes suddenly, and you can change the length of these things. And what happens if you listen to that? So this is what happens if you take the segments about a couple of 100 milliseconds long. Every syllable, you swap the thing. No way you can understand anything, right? Is this shorter? Still, you are screwing up basically on the level where people are the most sensitive. Slowly getting better, 100 milliseconds. Even shorter. Here we are already getting to the length which we are using in the short-term analysis, 20 milliseconds. Again, so we ignoring the phase of these segments. Whoops, what happens?
He thought, a lush divorcee at last.
So that may be what our recognizers are hearing when you use the short-time analysis of 10, 20 milliseconds. This is what of speech was.
He thought, a lush divorcee at last.
So the intelligibility is all gone from the segments which are on the 200 milliseconds, and gradually is decaying. I mean, for 100 milliseconds, about 50% of people can still figure out what has been said. If the segments are 20 milliseconds or 40 milliseconds, recognition is almost perfect. It sounds weird, but you can definitely hear the information. So what is telling you is that this is this critical integrating interval in human hearing, which actually cannot be screwed up with. Here, this is the cutoff frequency where the phase spectrum start becoming incredibly important. Here, in this part, phase spectrum of the signal is not that important, right? Magnitude spectrum is important. You can change the phase of every 20 milliseconds. It goes backwards now, and still you can understand.
He thought, a lush divorcee at last.
Relatively easy experiment to do, guys. I mean, you know, so, and it's, I just wanted to bring it up. This is something which would probably need a little bit more explanation, but Noah Cohen collected different experiments and was looking at the time constants which he observed in this, in forward masking, gap detection, equal loudness, just noticeable difference. You can see the time constants that goodness with which people could perceive the things were decaying, well, it was improving up to about a couple of 100 milliseconds. All these experiments, actually comes with about 6 different experiments, all indicate that there is this time constant of 200 milliseconds, which is there. So I believe that there is a temporal buffer in hearing, which is about a couple of 100 milliseconds, which of course relates to 4 to 5 hertz modulations. And so all these two things are related. I mean, the percept of modulations in sounds and the length of the temporal buffer, which we are observing in many of these simple psychophysical experiments. If you are looking into that, you will find it. And so this is pretty much all what I wanted to probably say. And I think that I'm running almost on time. I didn't allow much time for questions. I don't know if the master of ceremonies allows for the questions. I'm open, of course, but I think that Professor Ignan is already waiting in a line to take over. I don't know who is in charge.
Yeah, hello.
Yes.
Yes, sir. So we can take some few questions if people have, then we can switch on to Professor Ignan. Hello. Yeah, is anybody want to ask any question?
If not, it's okay. I can leave a little bit of time tomorrow.
Yeah, actually, I have one question, sir.
Yes.
Yeah, in one plot you have shown that when we are increasing that segment duration, that intelligibility getting decreased. So
say it again, please.
We have shown one plot where that we have increasing the segment duration, but intelligibility getting decreased.
Intelligibility.
Yeah. So that I not get it. Means
Is it this one?
Yeah. Yes, sir. Yes, sir.
Yes.
So when we increase that segment duration, that what I perceive that means intelligibility should increase.
No. What happened was that every segment which we picked up get flipped back in time. Okay. So essentially, what you were changing the phase 180 degrees of all the components in these segments over 200 milliseconds. So it means that every 200 millisecond segment which fits into this, what I'm talking about, this buffer of human hearing, gets screwed up.
Okay.
And suddenly it became very obvious that this longer time phase is actually crucial, and because the magnitude stays the same, right? Except the phases go backward. Yeah. But you flip the phase every 200 milliseconds, and intelligibility is gone. By 200 milliseconds, you hear nothing. You can't understand anything. If you do it for very short segments of speech.
Aha, he thought, a lush divorcee at last.
Sounds funny, but our recognizer seems to be reasonably happy with it. While our hearing is still can basically decode what's going on, right? So if you think about it, I mean, I know that maybe it's coming a little bit too fast, all these things. And if I had to live again, I would probably spend a little bit more time on the perception of sinusoids, a little bit more time on perception of more complex sounds. And maybe the next time I will be giving these lectures, I will spend at least half and a half, because I think I went here a little bit too fast. But the reason why I wanted to bring it up is that at least it makes you think. and makes you wonder if you want to improve the auditory, perception, processing of auditory sounds. Maybe we can start thinking about the things a little bit differently. My whole goal in life here is to convince you that short-time spectrum of speech is not a good thing to start with. And what we really want to do is to go back, again, through the sneak preview for my future lectures, is to go back to the old concept of speech, where speech is seen as a modulated signal in frequency bands. And if we do that, maybe we can get some advantage. I don't know.
Okay. Thank you, sir. Any else?
Yeah. So I have one question. So, sir, here we are doing this locally reverse speech. So, are we using this 20 millisecond, 40 milliseconds, this windows duration or segment duration to do the phase reversal? Is it?
Well, no. Every segment is flipped by
Okay.
180 degrees. So all the frequency components in this segment are the phase is basically negative of what it was before, right? It's flipped. So
Okay.
because what you really do, you take this is the original speech. This is the flipped segment. This is another flipped segment. It's just shown AB, but so you can see this is the opposite of this, right?
Yes.
This is the
Correct.
opposite of what
Yeah.
you see here.
Okay.
So you keep flipping each of these segments. So essentially you are saying, I think that what really is, if the phase in these segments was not relevant, then magnitude spectrum stays the same. If you just flip the thing backwards, right? And you continue concatenate these segments, short segments of magnitude spectra, you can recognize anything if the segments are long enough.
So is it conveying like this even if the magnitude spectrum is somewhat similar, still we are not able to recognize due to the shifting of the reversal of the phase?
Yes.
Okay.
Well, you cannot recognize. Sorry.
Yeah.
If
But,
the segments are very short,
Mhm.
magnitude spectrum seems to be okay for reconstructing the speech, right?
Yeah.
But if you start cutting into this critical interval, which you have in your head, 200 milliseconds, you better don't screw up the timing there. Because if you do, if you screw up the phase of these segments, you are in trouble.
Yeah. Thank you.
You can read this paper. You can
Yeah.
also read some comments to that, because this paper actually came out in Nature, got quite a bit of interest because people and people observe. I think there were some continuing efforts to verify that. You can try it yourself. I mean, this is one of the homeworks which we should have probably, if there's so much interest in it, this would be easy homework to do, or easy lab experiment.
Yes.
All you need is that wave editing software.
Yes. Thank you.
Yeah. Any other question?
Hello, sir.
Yes.
Sir, I have a question. Do you have any embedding present in amplitude envelope modulations regarding prosodic information in languages and dialects? Like, yes.
Well, clearly there's this rhythm of 4 Hz, 200 milliseconds is related to syllabic rate of speech, and you would expect that it may be related to prosody. However, if you speed up the speech, the peak doesn't really change all that much, surprisingly. So I'm not a prosody man. Quite frankly, I believe in changes in shapes of the vocal tract, not so much in changes in intensities or changes in fundamental frequencies. And this experiment has very little to do with the fundamental frequency, because the fundamental frequency in this in the spectra which has been used has been smoothed out. All we were looking at is the changes in envelope. So I wouldn't like to touch the issues of the prosody here, but you may think about it. But I tell you, the only thing which I can tell you is that we were hoping that we can use the changes in the peak of modulation spectra to discriminate between fast speech and slow speech, and you can't do it very well. I don't know, maybe we did something wrong. We expected that the peak will move more towards the lower frequency, higher frequencies, but we didn't see it. Certainly you cannot tell, because all these modulation spectra are long-term averages. So if you look at the individual sentence, you will not see such a nice curve, obviously. You know, it will be much, much, much noisier and much more dependent on the local structure of the sentence. But so you can, on the level of the sentence, you can't tell all that much.
Okay, sir. Okay. Thank you so much, sir. Thank you.
Thank you. Thank you for the question. Sorry that I hope that I didn't put down the prosody too much, but as I said, I mean, the prosody is of course interesting, very interesting carrier of information. But I believe the primary carrier of information are the changes of the vocal tract shape. How the vocal tract changes in vocal tract shape modulate the spectral components.
Any other question? Yeah. So okay, so thank you very much, sir.
Sorry for taking 15 minutes of Professor Ignanarayan's time, and I apologize. Didn't get the timing. Okay, maybe I will shorten up some another presentations. Okay, thank you.
No problem. We can manage.
Yeah, I hope that. Well, yeah, we can between us we can do it, right? Thank you. Sorry for this. Anyways, let me just stop sharing so that you can take over. Sorry for this. I think.
Okay, who is in control?
We can start, sir.
I can't hear.
We can start, sir.
No. Jagabandhu.
Yes,
maybe
sir.
we'll give a little break for people or no? I think they.
We can keep 5-minute break then.
Yeah, I think so. Maybe you can just.
Yeah.
Let us start at 12:20.
12:50.
Now it is 12:15, isn't it? No.
Okay, so 20 will start, sir.
12:20 we start.
12:20 will start. Yeah.
I think they should have a little break, otherwise, no.
Yes. Yes.
You should tell me when you're ready, and then I will start.
Yes, yes, sir.
Also, can you just check whether you are able to see my screen?
Yes, sir. We are able to see you.
You are able to see?
Yes, yes, sir. Yes.
What about this? You can see?
Yes, yes, yes. That's some Yeah.
That's all I need. So
Yes,
that's
yes,
fine.
yes.
Then it's okay. Okay, so let us start. Jayabandhu, is it?
Yeah, yes, sir. We can start.
Shall we start?
19. Yeah, well, 19. We can start, sir.
Okay. All right. So good afternoon. So let us continue our discussion. As I was present for the last few minutes of Professor Henig's talk, and I am glad to listen to that because while he's going from 10, 20, 30 milliseconds, 200 milliseconds, I want to go towards 10, 5, 2, 1, and so on. And it is interesting, probably because you are producing speech, and our objective is to analyze the signal to extract what is it that you are producing. You see, because it is a time varying system with a time varying excitation, and it so happens that the time variation, it is varying at every instant of time. In fact, we also assume that I will come to this a little later. So I think the stationarity and so on and so forth. So let us. So for this to understand the signal to extract the information of the production mechanism, whether that understanding and also the extraction of the production mechanism details are useful or not for various applications depends on your application, also your emphasis in the application and so on. So I'm not really addressing that part at all. I'm only, my goal here is signals and systems. I think I already told you already, signal and system, that is the theme, and we are talking about basics of DSP. Just trying to review which many of you might have gone through this course, but in a slightly different way. And also I want to you to be very careful in the terminology and also the way you articulate these things. You see, otherwise, generally the way we discuss or the way books given and so on, people just confuse, they mix up all the terminology and so on. That is what I want to emphasize the importance of understanding this and so on. And I'm fortunately lagging behind by 1 hour. That's okay. I think I would. And before I begin, any of you want to quickly ask something based on what we did in the yesterday's classes, or anybody wants to quickly ask something? And you can also comment on anything that you want. Don't feel hesitant on that, because the objective here is together we should make it happen. Something useful should happen. So, anybody any questions to ask? Okay, I am assuming that there is no response, and I will continue. And so, in the we are continuing on the basics of DSP. I hope I will be able to complete today, and it is likely that I may go up to 115 or 115 maybe. So about 55 minutes I'll take to rush through quite a thing. So what we have done yesterday, I think again, if you don't, again, and most of us feel that, oh, it's too much of mathematics, and there's nothing like that. All that you need is a basic understanding, and everything can be built on that. As I told you, we are talking about discrete time signals and systems, and because that's what we do for manipulation of a machine. And why do you want to do manipulation of a machine? Because of the flexibility that it offers. You see? And of course, that flexibility, you also have to pay some price for that. The price is somewhat, that's what we are discussing. What is it that you are sacrificing in this whole thing? In yesterday, this one, as I told you, any signal, speech-like signal is a function of continuous analog signal. And we said that first thing we are doing is action, a digital signal, and a discrete time signal. And then, of course, to compute anything out of it, we are talking about, when I say, although what we are ultimately ending up with something called Fourier transform, but otherwise we are talking about discrete time signals and system, we are talking about the eigenfunctions of a discrete time system, linear discrete. And these eigenfunctions happen to be alpha to the power of n type. And so we want to express everything in terms of alpha to the power of n, and not even that. We want to express in terms of what alpha being only e to the power of j omega n. You see? So a specific subset of this exponential. Why this is important? This is important because the eigenfunction of this. What do you mean by eigenfunction of this? Whenever you give that as the input for a linear system, the output also will be except that fact is a very in the process. You can see there is something which I explained yesterday, but I think you should remember this is not unfortunately highlighted well in books, although it is there. Please note that. So the output will be something like this: hn e to the power alpha to the power of 1 n hn. So if my xn happens to be alpha to the power, output also this, because h omega is independent of this. But this you can collect for different omega. For different omega. So this that means this system transforms this input into the same thing again, but with a scale factor. That's exactly what happens in eigenvalue problem and so on. That's why this alpha to the power of n. Somebody asked why exponential. Only exponential functions like this, where the time index is the exponent, this property holds. You see, so that is why it's called eigenfunction so on. And that is all that you need. All these transforms that are derived are based on the eigenfunction. We take a special case of eigenfunctions and talk about it. That is all. And you also notice the term, just as we said, exponential sequences like this alpha to the power of 1 alpha, as long as it's not function of n. And this is a, so this is eigenfunction, and also output you get is a constant into this. So this constant happens to be equivalent of an eigenvalue analysis. Okay? And it's also happen if you use that alpha to the power of n as e to the power of j omega n. And yesterday we discussed enough. I am not going to repeat that. We give the interpretation for omega. Of course, in this case, a normalized frequency. But normalized frequency, which I could have written this as 2 pi f by fs into nt. That's what I mean by that. So nt, what is t? T is equal to 1 by fs. 1 by fs. You see? So now you can see. So t is equal to 1 by fs. So if you see that, so this fs, something is wrong. No, it's okay. Yeah. T is equal to, so if you write like this is something wrong. I'm sorry. This is something wrong. Very good. Sorry. So if you write this as 2 pi f n t, where f is in hertz and t is in second, now 1 by t you can write it as 1 by t you can write it as fs, and then you can put it as in terms of 2 pi omega n, where omega is equal to, fn, where this I don't know, I'm struggling with the notation here. So omega will be simply normalized this one. I will write it. So I hope I have just basically what I want. Don't worry about all of this. I think it's just a point here is omega is frequency. That's all. You see, and normalized frequency. So because it is frequency, but for a given frequency, when you give this input, give value here, so you will see that h omega. Oh, sorry. This is again. I'm sorry for all of this. You have to correct while you are following me. If this happens to be e to the power of j omega n, this will be e to, please note that this is the way to write. You see? So the beauty of that is h omega. In the case of linear algebra, it is eigenvalue. In this case of system, it is some function of omega happens to be frequency, and it also reflects the spectrum. And some kind of frequency response or spectrum in some sense. We will come to that word later. So that means that's why these eigenvalues of the linear system represent some form of a spectral characteristics. That is the link between these. And I will stop that discussion on this. I just want you to understand the why this frequency term comes and why this eigenvalue. And so what is this eigenfunction relation systems and so on. That is the reason why I'm bringing all of it. Now, in the last yesterday's class, we said, when you come to we want to compute, let us say, I have xt, and I want to know, I want to project it onto the power of j omega t, and notice in both cases, the omega and t run from minus infinity to plus infinity. You have no choice at all. E to the power of j omega t, the moment you say that e to the power of j omega t, it's a complex sinusoidal function, and it runs from minus infinity to plus infinity. So when you want to take projection of any general signal onto this, you will get that projected value as x omega, and your x omega you combine with this again, you will get back this. That is the Fourier. But our idea here is my time domain signal is such that I cannot see all the features in this. For example, I said dampened sinusoid is the response of a dampened resonator and so on. But unfortunately, I cannot see that resonance and resonant frequencies here. Only when you see that project whole thing on e to the power of j omega t for different omega, you will get x omega. When you see the x omega and plot the magnitude of that, you start seeing the response. You see that it is omega. You start seeing it is omega naught. So that means at omega naught, this is what it is. This is important. This is what, of course, all of you might have studied this, but you will see we found the basic for today's discussion. So at the end of it, in order to take this signal and derive it, you can't do that, unfortunately. You see, because most of the integrals that are involved are not evaluatable at all. You can't evaluate any of them. So you go to take recourse to digital computation. That means you discretize this, and then even discretization is not a great thing, because you remember yesterday we said xn. Notice once I write xn, don't compare with xt at all. It has nothing to do with xt. So x omega has nothing to do with omega. This omega itself has nothing to do with this. Please note that, just very careful. And this is basically coming when I project this onto g to the power of j omega. You see, so this is for a discrete time signal. This is what you get, the output. Even this cannot be handled. Why? Because this, in order to get x omega, you have to sum this over all n. Minus infinity, which I don't have that luxury to do for more than, first of all, practical reason. Secondly, there is a physical reason also for that. You see, I will tell you that later. You can't have, because invariant system, although all we are talking about time invariant system, but speech production mechanism and a time varying system and so on. So this is what you have. So we start all approximation. That's what we said. First thing is discretization gives aliasing, and then you have to truncate it. Finite duration. Finite duration gives what is called not only resolution the frequency domain. I will explain that maybe a little later. And it also produces a side lobes and so on and so forth. So side lobe leakage it is called. Some ripple it will give. You see, that's a very really headache for signal processing people. You see, that is the problem, and we have no clue at all how to handle this in many signal processing algorithms. You see, and it has tremendous implication in the listen about the phase and so on. I will come back to the phase in the signal processing context. Then you will see that headache part now. You see, this truncation or taking a finite window spoils the signal. You see, the information completely, which is reflected more in the phase rather than the. You may say, no, ignore the phase. No, you can't ignore it all. You see, you can't ignore, and we will see that later. In fact, I hope I will bring a discussion on that toward the end of my this one. So now, what we have done yesterday, after doing all of this, and even if you take a finite duration, you are end up still a x omega cannot store, which you cannot capture, because omega is although it is period minus pi to plus pi. So that is why you need to discretize that. After discretization, you can get it by taking a closure of this one. But anyway, the point here is you need to force discretization here. You already forced discretization here, and truncation will unfortunately spoil the information, and you are not likely to get what you want to get. That is the point. Very, very important to understand. And so what do you end up here? Finally, you end up For a computational purpose, what is called the DFT pair. That means if you have xn of n samples only, that is take a segment of speech and so on of n samples, and so xn it is power of let me just write, let me write it as 2 pi n nk, and this one 1 by, okay, this is sorry, this is x omega, okay, and now you have 1 by xn 1 by n summation k is equal to 0 to n minus 1 x omega e to the power of j 2 pi by n nk. This so you can see this is equal to xn. So what it means here is that you do this, you will get x omega, and you take these values and do this. This is called a DFT pay. And in fact, very interesting that although we discussed so much yesterday, nobody is bothered about it anymore. You straight away talk a signal and take a block 100 times 10 milliseconds and go ahead and compute and collect the, sorry, I have made a mistake here. This is xk here. Please note, I'm sorry for this. It is xk here and the xn here, and this k is also equal to g is equal to 0, 1, 2, 3, so what is everything that you do is based on this. But if you don't know what this does, you are in trouble. You see, you are in trouble. What happens is you know somebody said this, so you use it kind of a thing. Oh, who is Oppenheim and Schaefer's book, you all of you know. Recently, about a year ago or 2 years ago, he wrote an article in Signal Processing magazine saying that these days teachers don't tell that the MATLAB effective algorithm, what is effective? Fast Fourier transform algorithm, doesn't compute Fourier transform. You see, that is, you must understand that is because of this DFT. Please understand that FFT is only an algorithm, and as a teacher, you should emphasize the fact that most of the time it can go awfully wrong. Okay? And a few implications also. This is the DPA. And of course, now a few quick properties I'm not going to discuss. This is why, as I told you, why we ended up here. This is for a computational convenience. And when you given any data xn, you block it. Block take and 20 millisecond, 100 10 millisecond at 10 kilohertz, it's only 100 samples. So my capital N is only 100. Or if it's 20 millisecond, capital N is 200. So you take that many samples, apply this, get the n samples and so on. The beauty of this pair of relations is you notice that both are periodic with period. Periodic also talk in terms of what is called a time circle and a frequency circle. A time circle and a frequency circle. What do you mean by this time circle and frequency? What it means? Yes, somebody.
Yes, sir. Today we are getting some network lag from your side. Your voice is breaking in between sometime. So if you can.
Maybe it is network problem.
Yes, yes,
anyway,
sir. Network problem only.
Keep asking. I didn't change anything, and it may be network problem, which we are not. We don't have any control. But anytime you can't hear, you please interrupt and ask. Okay. Please do that. Is that all right?
Okay, okay, sir.
I think I am somebody posting sometimes it's not coming. Network is streaming is not smooth. Is there anything from my side or from your side or both sides? I don't know. I have no idea.
No, sir. I think your network today, your network connection is not.
Yeah, we
it's
can
not
able to
good.
hear,
No.
sir. Suddenly, sometimes some glitches are coming, so maybe that is due to internet.
Yeah, I can see that. In fact, it's not that high. You see, I can see that.
Yeah, it is
But
fine somehow, but yeah, in between sometimes some
but
glitches
anyway,
are
we
coming.
have to.
So
You
we
see,
can go ahead with that.
we have to go
Everyone can
ahead with
have
it.
sense.
Please interrupt me,
Yes, yes, yes.
and I will repeat whatever I have said and so on. To cover certain portion or something like that, it is to uncover a few concepts in the whole presentation. That is the whole idea. So don't worry about some point, some portion to be discussed. It doesn't matter. Whatever is discussed, if you understand, that will be fine. Okay. So I hope as of now you are able to understand. Okay. Jagabandhu, can
Yes, sir.
you hear me?
Yes, 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 sir.
Are you
But
okay?
yeah, so I
Okay.
think, can we, sir, do one thing? Maybe can you log out and log in again?
You want me to do that? I can
Just
do
if
that.
we can do that, if we'll see that resolves, that's fine.
No,
Otherwise, we will.
what I am noticing is not that high as it was yesterday.
Uh-huh.
Your wireless link
Yeah, it's not that great is coming. It's lots of
is
lagging is
slightly
coming.
lower today. So yeah.
So just
You
we
see,
can.
it's raining quite heavily here.
Yeah,
Sir,
yeah, that is.
sir, also one thing if you can just switch off the video camera, maybe it will save some bandwidth. So
Yes,
that
yes, yes,
if that
yes.
can help
That
you.
option we can take, sir.
I'm not too sure, but I can do that. But the point here is, although we are talking about speech and speech signal processing, it is the audio video that conveys message better.
Yeah.
Because you will be watching my lips movement and facial gestures and so on. So even if you are not able to listen to the audio better, this can substitute for the missing part. I think let us have the video, and unless you feel I can switch off, but I don't know. You want me to switch off and see?
No, sir. I think we can go by Jagbandhu's this thing input, wherein if you can just log out and log in, I think it may help us. Like, yeah.
I will try that. Then all of you hold on for a second. I will do that. Point here is the weather is very bad here. You see, in Hyderabad. So from where I am speaking. So even if I do that, I am not 100% sure. You want me to switch off and switch on again? Somebody?
Yes, sir. If you can, log out and log in.
I am doing that, and let us hope that. I hope at least can you hear me now?
Yes, yes.
Yes, sir.
Hello?
You can share your screen.
Hello?
Yes, sir. You are audible. We can able to hear you, sir.
Can you hear me?
Yes, sir. We can
Can you
able to hear you.
repeat?
Yes, sir. We can able to hear you, sir.
Oh, you are able. Okay, fine.
You can
I
share
think
your
let
screen,
us
sir.
go ahead with this. I think I will. I know because I feel that video will be better because the reason is that will help you to substitute any missing part in the audio. That is the point. I think.
Yes, sir. You can share your screen, sir.
Shall we go ahead?
Yes, sir. Yes, sir. You can share your screen, sir.
Yeah, that's what I am struggling to figure out what to do. I think I have to do the sharing of this screen. 1 second, I will do this.
Yes, sir.
Sharing the screen. How do I do that? I don't know. I'm not getting some thing somewhere. I don't know.
All test you can.
I think I am starting again. I am quite
Okay.
possible that. I'm not getting that. How do I share this? That's what,
Share screen option.
Okay, okay, I got it. I'm okay. Yeah. Is that okay now?
Yeah. Yes, sir.
Yes, sir.
Sorry for all these disruptions and interruptions, but I don't know how to handle this. Okay. So the important thing here is, I think one of the main things which many people get confused is this idea of any computation that you make in this, becomes equal of the DFT type with a block. It becomes what is called data organized in a form of a circle, time circle and a frequency circle. And what it means, you can see that's why 2 pi by n it is coming. That means you divide this 2 pi into n intervals, call this as 0, 0, 1, 2, 3, etc. This is my n minus 1. And likewise here also 0, 1, 2, 3, 0, 1, 2, 3, etc. And each interval is 2 pi by n. That's what it is, you see. And this is n minus 1. So what do you mean by this xn and xn mean? On each of these points, you put a stick of height xn value. You see, x0 means a stick of that height h0, like that, And likewise, the result xk, you put it as this. Because xk happens to be complex, you need 2 circles, real or one complex stick, you may want to call it. Put it on each of these points. That's one. This concept is very important because I noticed many people writing programs, at least at the student level, the first level of program, they get wrong results because you don't take this factor into account. And why did you end up here? You ended up here because of the operations that you have to do to bring it to a DFT form with all the assumptions that you make. And you remember in the first part of my lecture yesterday, I did mention every signal has to be specified from minus infinity to plus infinity. Here also, although you have taken a block of n samples, notice that you have specified from minus infinity to plus infinity. How did you specify? Once you put those n samples on this, you can go around the circle any number of times. See? And so infinite number of times, that is how, that means you made the signal periodic here. And similarly, xk also periodic. And it is this periodicity property, apart from the whatever deficiency that you have in this, but this periodicity property also gives some advantage one can exploit, and that is what is exploited in computing this through FFT algorithm. I'm not going to discuss that. So direct computation of this, because for each point you need n multiplication. For n points, so your direct computation is n squared operations, n squared multiplication. You see, and whereas FFT algorithm gives n log n. That is the idea. And I am not going to, that is because of the symmetry properties, the circular properties, and so on. You see, and there are many other interesting properties of DFT. I am not really going into those details. And so now, with this background of this, now we will move to, until now, what have we done here? Everything hovers around this first diagram I wrote, xn, yn, and hn. That is and this is a discrete time system. and of course linear time invariant discrete time system. This is all everything over there. So now what did I say there earlier? If I give delta n, I will get Hn. That means since delta n itself doesn't have any relations in the sequence, Hn represents the system completely. That's what we say. You see, and likewise you can see if I had given e to the power of j omega n, I will get this becomes h omega. And I'll output also will be e to the h omega, e to the power of j omega. Okay. So this is what it. So what are now you see we are got Hn is a unit sample response of the system. H omega for different omegas covering the minus pi to plus pi. Again minus pi to plus pi. Why? Because the discrete time signal is always you get everything periodic. That means if you make omega and omega plus 2 pi, it is same value. So that is why it's a periodic here. And in a discrete time system, this is what you get. So H omega for all omega, that means in the range minus pi to plus pi, also represents the system completely. It's not enough. Already, why do you? So we are now talking about different representations of the system. Different representation of the system. When I say discrete time, linear time invariant discrete time system. So one representation is of course Hn itself. Another representation is H omega. At another representation of this, you see, these are all nice to write, but for most physical system models of you see that this Hn, even though you do delta n and so on, Hn turns out to be infinite. It goes on forever. You see, just as, for example, yesterday when I tapped this table, you remember, and it gave some response. So, excuse me. That response still is there in it. It has not vanished anywhere at all. You see, only thing is that response died down so low you cannot see that. So the response of any physical system goes on up to infinity. You see, please note that. That is very important. So if that is the case, you don't know, of course, no problem. But for different signals, you have a different. So that is why it is difficult to represent this. Okay? Although if it is a closed form expression, there is no problem. But if it is a sequence of numbers, you can't represent it. Unit sample response of a discrete time system cannot be represented exactly because it goes on up to infinity. You see? Likewise, its response that you have H omega, which you know we have written, this is nothing but Hn e to the power of minus j omega n is equal to minus infinity to plus infinity, of course. So if this is what you have, so even H omega, Hn you can't represent it. H omega for omega is equal to minus pi less than omega less than pi. You can't represent H omega also because there are infinite number of values and so on. So, but then how do you design a system? How do you implement it and so on? That's it. There is another representation, what is called the linear difference equation representation of a system. So this simply says yn, okay, is equal to minus of ak yn minus k plus bk x n minus k, where k is equal to 1 to, let us say, m, and here k is equal to 0 to m. So notice what I have written here. You know, it takes some time to understand, but it's very simple. All that I have written here, this is called the linear difference equation representation, where you have m ak and n plus 1 out of that B0 you can make m A case and n B case will represent the system completely. So that means from this infinite represent the system in terms of A case and B case. You see? And so to this is called the linear difference equation representation. Suppose in this your xn, if you give delta n, your yn will be automatically hn. You see, and so if your xn is e to the power of j yn, you will automatically get that one. We are going to see that. So this is a more implementable form of a system. You see, for a given input, you can get the output, provided you know A case and B case objects. You see, and you may say, why is it relevant in speech analysis? From the speech signal, your objective is to derive this M A case and N B case, so that you can represent the system. That means in terms of M plus N values, you are able to represent the system, finite number. And you can also generate the signal by means of this. That is the idea. And so this is called the linear difference equation representation of system. And we can, out of this, we extract another representation. Or what do you mean? What do you mean by that? You remember yesterday, although I didn't elaborate, there is a G transform. What do you mean by G transform? Any signal that you have, let me put it like this. Indeed, so if you have xn, instead of taking a projection onto e to the power of j omega n, projection on what is called the e to the power of j omega, take a projection on g power minus n. So xn, take the projection on g power minus, where my g is equal to r e to the power of j omega. Okay, I discussed this. So earlier we talked about r is equal to 1, but now we talk about r is any r kind of, because this covers the entire two-dimensional space for different r, different omega. I suppose if any of you doubt in this, you ask me, because everything today, the rest of your discussion follows this, uses it. So now instead of this, you follow, all that you have to do is, now you take the projection of this onto this. What do? Multiply with the summation over n. You see? And n is equal to minus infinity, this becomes x. This is called the Z transform of the given sequence. And the beauty of this is just as you had just as x omega, you have xg, which is more general than x omega, because you are using r instead of constraining yourself with r is equal to 1. You see? So this G transform is a projection of xn onto g to the power of, this is called the G transform. And for all values of n is equal to minus infinity plus. So the beauty of this is, I am not going to discuss that in great detail, but if you have a signal, shifted signal xn minus k, you can easily verify and show that its G transform will be z minus k xc. That means it is, so this is the result which you can easily derive from this definition and so on. So again, when given xg, you can reconstruct the signal. So when it is a delayed signal, this is what you get. Using this knowledge here and substituting, that means multiply both sides with g to the power of minus n and sum it over, you will get the following. I am not going to do that. It is a, most of you might have done in the, so what you do in this process is, you bring this part to the left side, and then you can write that. First, let me write that. You can write it as ak y n minus k, y n minus k. Now k is equal to 0 to m is equal to, this one is k is equal to 0 to n bk x n minus k. Notice that both of them now start from 0, where my a0 is equal to 1. That's all. Okay? A0 is equal. So in this form, now you multiply both sides with g to the power of minus n and sum it over and do that. I am not going to do that. All of you might have done it before. That will take the projections of this and so on. You will get the following. That is ak G minus K, okay, AK G minus K, YG, K is equal to 0 to M, and this is equal to K is equal to 0 to N, BK, G minus K, X. I'm just, somehow there is too much of a wind here. I'm not able to control that, but can all of you see this? I think so. What I have done here is whatever is needed. I'm just trying to adjust my paper to show you. So this is a linear difference equation representation and linear difference equation representation. And I just said the G transform. It is a production of xn on G to the power of n. And then you will get a delayed signal. You will get a G transform. I put this logic into this. And before that, you write this equation in this form. And then you will get this. Now you notice that YG and that XG are independent of K. So you can write YG by XG exact as the summation BK G minus K by summation AK G minus K, K is equal to 0 to N and K is equal to 0 to M. Before I proceed, this particular ratio is called HG. This is what is called the system function. System function. And we are going to spend quite a bit of time. We use it in speech analysis extensively. So I want you to understand it. Basically, what I'm saying is there is a now we are talking about 4 representations. One is HN, unit sample response. Another is H omega. For want of a better name, call it a frequency response system. And third one is a linear difference equation system. Fourth one is in terms of system function. Notice that you can build a system function completely by once you know AKs and BKs. So if given AKs and BKs, you can build the system function. And once you have these AKs and BKs, you can also write the difference equation form. And once you have the difference equation form, you can get HN. And how do you get H omega? H omega you will get, it is only a special case of this where I'm going to write here H omega. I'm a little sloppy in my notation, but it's okay. I should write it as J omega, but I'm not writing it. E to the power of J omega, I'm not doing that. So this is a very not a good notation, but anyway, to simplify. So when you evaluate this Z on this, that means then you will get H omega frequency response. So these are the important representations that we have. And now we'll discuss more on this H omega, the HZ. So we have HZ, and all of you have studied this in great detail earlier, and just want to, this mostly a review kind of a thing, but with some additional interpretation which you may not have studied. You see that, sorry. K is equal to 0 to n minus 1. Oh, sorry, n. N, and here K is equal to 0 to AK. Before I proceed further, you see, this is called a system function, defines the system completely. And you can see most of the speech analysis in particular, and in general, most of the signal analysis, speech analysis, your objective here is given the signal SN, how do you determine the JKs and BKs so that I can model the system that is derived from the signal? That is the idea. Please note that. That is the reason of doing this. And notice that Hz, what is Z anyway? Z is nothing but this is called a Z plane. And you can see this G plane can be covered completely by using R and omega. If you give me R and omega, for different values of omega, you for a given R, you move around the circle. For different R's, you will cover different circles. And through that, you cover the entire plane, G plane and so on. So since you can cover G plane by giving this G, any value of G, which is a complex number, expressed in terms of R e to the power of G is R e to the power of j omega. You see, R e to the power of j omega. So given this R omega, you can get any value. So that represents a point in this plane. You substitute that value here, you get one Hz. And it so happens in G is complex, Hz also is complex. You see, so you have a complex thing. If you want, you can write a real image part, but let us not do the worry about it. So getting this Hz for all values of Z, that means you are able to get the Hz for all values of Z. That means an infinite number of points in this plane. Even though you have only finite number of values of bk and ak. That means only n plus 1 b0, you can always scale it out. So n plus m values are enough to describe this Hz completely. This is a very beautiful thing. That means basically what it means is finite number will describe the entire response of this. And also in this, when you substitute G is equal to Hg, G is equal to e to the power of j omega, that's what we said, then you will get h omega, I told you. You see? And what it means, what is it? Evaluating this means, that means you are, although you have infinite number of values, for every z there is a value and so on, you are only considering the values along the circle. How do you do that? Now you have to, I give what is called usually a tent analogy, a tent or shamiana, for example. I have all of you know what is a tent or a shamiana. So how do you build a shamiana? You put some poles, hooks and this poles and also some pegs and so on, and you create a shamiana shape and so on. So my Hg is the shamiana shape. And what you are talking about is values on this means, take the shamiana and put a unit cylinder for like this, a cylinder with a unit diameter radius, and then place it at the origin there. So whenever the shamiana cuts this, that is my h omega. That is my h omega. So that means for h omega, if you want to call it as a Fourier transform of a discrete time signal, that is obtained from Hg. It is only a subset of that, and it's obtained by just taking the intersection of this unit cylinder of the with this shamiana. So that is the. So I suppose you got that analogy clear. And now another very important thing that we should see here is, you see, this is a polynomial. This is clear, some mathematics, unfortunately you can't avoid it, and but very important. Suppose how many coefficients are there? N coefficients. So the roots of this nth order polynomial, the roots of this is, there are the n roots for that. Here there are m roots for this. The n roots of this are what are called the zeros, n roots of numerator. Because why? At each of those roots, Hg will be 0, isn't it? Because what do you mean by a root? G minus G1 into G minus G2 into G minus G3. If you keep writing that as a product of the individual root, whenever any one of them equal, then it will be 0. So that is why at these n roots, any one of these roots, it becomes a 0. That means the roots of the polynomial of numerator, n roots of numerator, they are called zeros or zeros of the system function, and m roots of the denominator or what are called the poles. What do you mean by that? That means if just as you have here, if they have m roots here for this polynomial, at each of those roots, that means when denominator is 0, what happens? When denominator is 0, Hg becomes infinity. Okay? So this is so that's why they are called poles. Just a crude but good analogy to understand. So a finite number of poles and a finite number of zeros will describe infinite number of values of Hg. That means you will get the shape of the Shamiana by just identifying. You don't have to do anything. Give the location of the place where it is 0 and location of the place where it is a pole, and then the entire shape of that is decided. You see, so it is one way to look at it is Shamiana or a tent. If you see where see Shamiana just by pole means real pole. Let us say you take, and you don't put pole everywhere. You put enough number of poles so that it doesn't sag. And just to having poles, can you retain the Shamiana? No. You need to pull it and peg it somewhere at it. So different points you peg it. So the location of points where you peg in and the location of points where you put a pole will decide the shape of the Shamiana completely. You see? And that is the beauty. So now the whole idea here is, even if you change one pole, the entire shape will change. You see? That is the important. So you can also look at this HZ as in terms of n poles and n zeros and m poles here. And the location of that will give you the entire response. So you can also say, once you get that new response for any location of poles and zeros, you just take the cutting intersection and the unit cylinder, you will get the frequency response. And this is exactly what we do in speech analysis. In speech analysis, you will be surprised to see that this that is used in understanding and also extracting information or interpreting the information. So I suppose all of you, I want to pause for a minute here. I may take another 10 minutes, but before I proceed further, anybody wants to quickly ask something? Anybody? Most of you would have lost interest in these equations.
Yeah, Ganesh, you can ask.
Yeah. Yes, sir. Sir,
Yes,
what is
Ganesh?
the motive? Yes, sir. Yeah.
You have to unmute your mic. You have to unmute it.
Yes,
Yeah,
sir. I have one.
please.
Yeah. Am I audible, sir?
Yeah, you are.
Sir, what is the motivation for AK and BK in the linear difference equation, sir?
What is the motivation for a good question? See, no, it is AK in the linear system completely. You see, provided you can derive that AK. See, all I have is only a signal. You see, and from the signal, if there are finite number, but you can still derive the characteristic of unit sample sequence and so on. So that is the idea. You see, you understand? So the number of coefficients that you need to represent a linear system is finite. That point. Okay. Is that clear?
Yes, sir. But in practice, we don't have this AKs and BKs, right? We just have the system response, right? So then, how does this affect with respect to inputs?
Good point. Yeah. See, the whole purpose of signal processing is to derive AKs and BKs from the given signal. From the given signal, all that we have is external. So from that you have to derive AKs and BKs. That's what you are tomorrow or day after tomorrow's class. You see?
Yes. Okay, sir. Yeah. So like, yes, sir. So like my assumption is like if our AK and BKs are proper, then only the system response or whatever we infer, that would be right.
That's very right. You see, that means, you see, again, remember what I said in yesterday morning or in the first class of this course. What did I say? A signal has some information in the sequence of this, and that information is about the unknown system. I want to pull the characteristic of that unknown system from that signal. So one of those is So as much as possible about the system, I want to pull out from that. How? In fact, probably the only effective way of doing is that is how to determine these A case and B case to, for example, just to since you asked that question, so we are given the speech signal. If I extract those A case, let us say some number 8 or 10 or something, they represent the resonance. The every of them represent the resonance of the vocal system.
Sir, sorry to
Every
interrupt. Can
pair.
you
So if you
repeat
give, let us say 10,
sir, sorry to
m is
interrupt.
equal
Can
to
you
10.
repeat the thing again? Like, what does, I mean,
Yeah, I will
yeah.
do that. I will do that. Please. In fact, I am going to do this right away anyway. Since you are, suppose you see m is equal to 10, just for the sake of discussion. So,
Okay.
because you also know that these roots, when I said, all the roots are in the Z plane, you see. But it so happens since AK and BKs are real, this you would have gone through an algebra earlier also. AKs or BKs are, what does it mean? What it means is either the root is on the real axis, or if it is away from the real axis, it has to appear in complex conjugate. That means, because you know quadratic equation, A square, I suppose all of you know that. So if A, B, C are real quantity, then the roots of them will be either real or they have to appear in complex conjugate. Is that clear?
Yes, sir. Yes, sir.
So that logic you have to use here. So if the roots of the denominator polynomial, either they can be either on the real axis, or if they appear away from the real axis, it has to be in complex conjugate pair. It cannot stand alone. Because if it stands alone, then A case and B case cannot be real. So for real coefficient, that is the constraint. Okay. Now what I am saying is every such pair that you have, let us say one pole pair, one here and another here. If you have in the complex conjugate pair, that may mirror impact. That represents one resonance of the vocal tract system. You see, and you can have a different for let us say for a number m is equal to 10, you can have maximum 5 resonances. You see, and those 5 resonances you need to derive them. Once you can derive them once from the A case, and in the A case you can derive from the signal. That is the beauty of it. So signal you can derive A case, and from A case you can derive the resonance frequencies and its bandwidths. And that is how you represent the vocal tract shape.
Yeah.
Capture the vocal tract shape. Is that clear?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
We are going to derive this in the next class. We are going to do all of that in the next class.
Yeah. Okay.
Do you understand significant? Likewise, you may say, what is the B case? That is, I talked only about the A case. Because that is the denominator polynomial means it's a resonance. You see, that also will do. What about the zeros kind of a thing? Zeros is like an anti-resonance. When I say anti-resonance, it is something like this. For example, when I'm saying ah, sound ah, you can see I have closed my nasal tract, and the only sound is coming from the oral tract. So it only gives the resonance of the oral tract. On the other hand, if I say instead of ah, I say ah, ah. I hope you can make the distinction. What am I doing in the ah? I am allowing the nasal tract also to play a role. That means I open the velum and let the nasal tract couple with it. That nasal tract coupling, when you are listening to only oral tract, okay, that is called anti-resonance. Anti-resonance means that can be represented not by A case anymore, it can be represented only by B case. That means the resonance of the nasal tract, it is there will be a null, not a at a resonance there will be a frequency signal. You have to find an mechanism or a method to determine both A case and B case so that you can see, you can capture both the resonance and the anti-resonance. Do you understand that? I suppose.
Yes, sir. Yes, sir. Yes.
Okay.
Got it. Thank
So
you, sir.
this is the significant. So basically system function depend by AKs and BKs. These can be the roots of this. Let us say if you want to design a system, let us say this is my G plane. You give me positions like this, let us say, and something like this, and then here, here. So what I have done is I have given some poles. Pole means a cross, and zero means it is a zero. I have given those locations. Let us say it can be somewhere also here also. No. So, but notice anything away from real I have to be in pair. You see. So you give me the. I can. How do I get it? Simply this polynomial. You see, and likewise both the numerator and denominator crosses will give the denominator polynomial and zeros will give the numerator polynomial. So it is interesting if you want to represent a vowel R, if you know the resonance, you see, I thought I will give an exercise today, maybe in the afternoon I am going to give you an exercise for you to play with. So if you give the locations, you can, so for R, the locations will be different. For E, the locations will be different. So by giving different locations here, you can get these corresponding, go to the difference equation, substitute those AKs and BKs, and give Xn as Hn, and derive that you will get the response of speech that vowel sound. Okay? I suppose you understand. So that is the significance of all of this. And and now I think my time is up in the sense that all of you have to break for this one. So afternoon, I am still not done with it. So we will take a of location and then show how they look like. That will help us to understand and the speech part of it well. Okay. So I will stop at this point, and if you have any quick questions, you please ask me. Otherwise, we'll meet after lunch. Okay. Let me see. What is the motivation for AKs and BKs in the linear difference equation? Yeah, I think I explained that. It was Ganesh who asked me. Yeah. Anybody else? Any question? Take it easy. I know all of you will. These kinds of you want to see some colorful slides and some experiments and some plots and so on. Most of the time, as engineers, those things are nice to listen like a story. But the point here is, if you have to design something, you have to get to this part of it. The goal of this 10 lectures here is at the end of it, you don't like write the speech signal waveform and explain the way people who do not know explain, because every waveform, every speech signal waveform has some information to carry, and that you should be able to appreciate and derive it from the signal. You see? Yeah. Anybody has any questions to ask? Any other questions? So if there are no further questions, we can discuss now. Yobandhu, is it all right?
Yes, sir. Yes. Hello.
Huh?
Yes, sir. Yes.
Louder.
We can. Yes, sir. We can close now, and we can meet again at 2:30.
2:30. Okay.
Yes, sir.
Please inform them, and then we will meet at 2:30. Okay. I am closing it. All right.
Okay. So thank you very much, all. We will meet at 2:30.
Able to hear me, sir?
Yeah, yeah. How about you?
Okay. Yeah, very clear, sir.
Oh.
Yes.
Because morning they said there is some network problem. I don't know.
Oh,
But anyway, there could be some problem from this side because the weather is very bad here, and also maybe the network wireless strength also a little low. I think.
yes, sir. Yes, sir.
Now it is okay for you. Or?
The same, sir. Weather condition here also it is very bad, sir.
Oh.
It is raining continuously and
Here also.
drizzling.
Anyway, for the schedule, I am lagging behind by one class.
That's perfectly fine, sir. We can.
I think I'll make it up because I don't know how to. I can make it faster by skipping or most of this, but I'm worried that they will never be exposed to this.
Yes, sir. Yes, sir.
So.
Maybe we can start, sir.
I'll do that. I think I'll. Okay, so.
This meeting is being recorded.
Let us continue with what we were discussing in the morning. But before I start, I would like to see if any of you want to ask or say something. You see, whatever you want to ask. I'll just give 2 minutes for that to see if I can, 1 or 2 minutes to see if I can get any response from anything you want to ask.
Any of you have any questions?
Questions, comments, or criticism, anything?
Am I audible? Hello?
Yeah,
please.
Professor, I had one query regarding that representation of a system function, wherein you mentioned that all the system is represented by BKs and AKs.
Right.
And so how is that the entire, you mentioned that the entire Z plane could be is covered through the system function. I mean, you gave an analogy of a cylinder.
Right.
So can you please explain that once again? I mean, I couldn't hear that.
Sure, definitely. Yeah, I'll do that.
How does the system function cover the entire Z plane? That part.
Yeah. Anyway, yeah, I will do that. Since you asked me, I'm just projecting that part only here to, you can interrupt me while I'm presenting so that I know whether you are catching me or not. You see, up to this point, is it okay that how do you get the HZ?
Yes, sir, that's fine.
Right. So HZ is what is called the system function, which defines all the characteristics of a system completely. It is another way of representing a system. And so now HZ, if it is written as the ratio of two polynomials, you see, and which are defined by AKs and BKs, there are only n AKs and m BKs, or m AKs and n BKs. So that will describe HZ completely. What do you mean by that? So Z is a variable. Z is a variable representing any point in this plane, two-dimensional plane, any point. You see, you can talk in terms of real part, imaginary part, or r and theta. Both are same, isn't it? Real part means r cos theta, imaginary part means r sin theta, or r sin omega. Sorry. Okay. So any point in this G plane can be represented as some value of r, some value of omega. Is that clear?
Yes, sir, that's clear.
So if that is the case, substitute for a given AK and BK, substitute that value of Z here. Or e to the power of j omega for a given r and omega, you substitute that here. So you will get one value of HZ. Am I right? Is that correct?
Yes, sir. Yes, sir.
Now you can do that for every r and omega in this plane. Then means you can get HZ for all values of infinite number of values in this plane. Clear?
Yes, but you also mentioned that when everything is done, HZ would be in the form of a circular ring. Is that something?
No, I know. You see, you can, as I told you, if you write this as r cos omega, r sin omega, that will be real part and imaginary part. Am I right? Is it okay? So by giving the real part and imaginary part, you can locate any point in this. Or the same point can also be represented by r and omega, either way. One is polar form, another is just a rectangular form. You see? So given any such point in this G plane, you can get HG for all values of G. That is the point. You see? Now, all values of G, you are getting this once you give these AKs and BKs. How many values are given? You are only giving m plus n values. Giving m plus n value describe the system function completely. That means for infinite number of values, you have for all points in this plane. You see? And on top of it, you see, I said H omega. How do you get H omega? H omega is only a special case where you make r is equal to 1. If r is equal to 1, what you have is e to the power of j omega only. That represents the circle, unit circle it is called. A unit circle, okay? So out of all the values of HZ, collect only those values which are lying on, for points on the unit circle. You see, that means notice that HZ, that every point HZ is like a value, let us say stick or something. So you have infinite number of values. Only take those points on the unit circle. You will get H omega. Omega ranging from -pi to +pi or 0 to 2pi. You see, that's what I. So 0 to 2pi. This is now take a cylinder of unit this one, circular cylinder, and just place it at the origin. What happens? This whole HZ values over the infinite space, it cuts the cylinder, at some point along the circle. Those values, that means from the plane to that height, will be representing H omega. That is called Fourier transform of that. Is that clear?
Yes, sir, it's clear. Thank you, sir.
Okay. Now, although I still have to take some more time to complete this part of it. Now, what we will do is the following. I will talk about what is called, this is all the background we discussed yesterday and today is to understand this part, what is called the equivalent representation of signals and system. What do you mean by that? So far, we have talked about Hn, unit sample response, H omega, we call the frequency response of the Fourier transform of a discrete time signal, that is of Hn. That is frequency response representation of system, which I can obtain by just taking the Fourier transform of this, or linear difference equations, AKs and BKs. Linear difference equation representation where the m plus m coefficients are given, or system what we call HZ. What is called from HZ, you can see I can write numerator polynomial as product of several first order and second order polynomials. Why? First order polynomial means the roots are on the real axis. Second order polynomial means the roots are in the complex conjugate location. So, but all the coefficients are real. So you can always split the polynomial into a product of several first and second order polynomials. And so that means, and each one has either a pole or a complex conjugate pair. So I can also say that locations of poles and zeros also is a complete representation of why. Once you give the location, you can get HZ. Once you give HZ, you can get H omega. And once you give HZ, you can also get Yn, Hn, because the difference equation you can use and so on. So this is what, so that is what we are going to discuss now. This is called the equivalent. You may say, why are you boring us with so many representations? Why can't we deal only with one? Each representation has its own significance. It will be useful in different contexts. That's all. H omega will help in explaining the system side of it. A case and B case are useful to use in a different linear difference equation to synthesize the signal from a system or generate the signal. HZ will is used again to represent the system in terms of the poles and zeros are used to design the system. To design the system means I want a resonance at a particular frequency. I'm going to give that in another 10-15 minutes. So given some resonances and bandwidth, I can generate A case and B case. Given A case and B case, I can generate this HZ and so on. That is the way it goes, you see. So let us study all of this for specific cases. So I will start. So all this is called the Z plane. So you have a Z plane and you have a unit circle as a reference. This is what I have. So this is my Z plane and unit circle. This is the origin and so on. I suppose this you got. Now what I will do is the following. I just consider a pole pair. This cross means pole. That means this is equal to my HZ. I'm not going to, it is equal to, numerator is 1 because I have not put any zeros here. 1 are constant, it doesn't matter. So this will be something like 1 plus A1, G minus 1 plus A2, G minus 2. Of course, somebody will ask, why G minus 1 here? I am writing it as a polynomial G minus 1. Basically, this is the standard representation. That is now. So basically, when you write it in Z, then what happens is there will be Z squared in the numerator. So for all of these, there will be some poles or zeros at the origin. There is a normalizing factor. You can ignore that. So the otherwise, this this different represents one complex conjugate pair like this. That means given this A1, you solve this quadratic, you will get a pair of complex conjugate roots. Let us say those are the roots. Or given the root, you can construct a quadratic. My polynomial variable will be Z minus 1. I see that's what we use most of the time because it's of Z. You can use Z of Z. The automatically comes out of this if you just put Z square, Z is some power of Z, which will represent only the roots at the origin, which we ignore. You see, we don't have to consider that. So, so let us consider this now. So this is the G that domain represents. That means given this pole, what does it represent? So what it represents, how do you know? Suppose these are given. This is R and omega, let us say. These two are given. So what does this mean? This is minus omega and this is R. That is the complex conjugate. That means this is R e to the power of plus minus j omega. See? That is the meaning of it. So R e to the power of plus j omega is this point, R e to the power of minus j omega is this point. And as I told you, it has to be conjugate, that means mirror image around it for the roots to be. So given this R omega, you should easily be able to get A1, A2. I suppose you know what to call this as Z1, let us say, and this is Z2. Write Z1 minus Z2 into Z1 minus Z minus Z1, Z minus Z2, and expand that, you will get this, the corresponding A1. So that is what it is. Now, for this system, now let us plot what is called the at Hz at g is equal to e to the power of j omega. Okay, that means along the unit circle. This gives me the Fourier frequency response h omega. As I told you, this notation is a little sloppy. It doesn't matter, let us not too much worry. So this into e to the power of j theta omega. Theta omega. So that will be my h omega. So now for this, if you plot this h omega, you see, this is what we will get. I see this is my omega, this is 0 to pi and 0 to minus pi. Somebody asked negative frequency. It is only a convenience, otherwise it has no great significance. You will automatically get it, and in this case, it will be symmetric and so on. So that means if you have this omega, in fact, for me, it's convenient if I write this as omega naught, okay, omega naught, so that you will get this at h omega. This you substitute this, you will get h omega, and the root that is given is at j plus. So what is the significance of this? So if you now plot this h omega as a function of omega, this is what you will get. In fact, all the discussion since yesterday is only to bring you to this point where this is my mod h omega, magnitude response. So as I told you, because this is whether it is symmetric, it will automatically be symmetric. There is no problem. No? This is my omega naught minus omega. So you can ignore the left hand part of it, but I am writing it to make it complete. And notice that my h omega is always periodic. So and also since we are talking about a real system and so on, this will be symmetric in this case. So now this is the frequency response. Of course, you may also ask the phase response. It is very important, but a lot of people don't like it. But don't like it means it is a little harder to understand. What happens here is, I will just to trace it. It is it takes some time for me to explain, so I will not explain that. So this is the omega naught, and this is omega naught minus omega naught, and this is my theta omega. Okay. And what is important here is, don't worry about the shape of this. And now, if you take the negative derivative of this function, it will look something like this. And recently, a lot of people are using even in practical systems as well. So this is called tau omega, which is nothing but minus d theta omega by d omega. So this tau omega looks almost like h omega, except that it will be sharper. That's all. Location of peaks will be exactly at the same kind of a thing. So this tau omega, this is called the group delay function, and this is the phase response, and this is the magnitude response. Okay. So you see what I have done here. I given these roots, I will repeat once again. Given these pair of roots, that means omega naught corresponding to the frequency that you want, and R correspond to the damping. It is basically it's a resonance frequency, the damped resonance. So this is the frequency. R displays the damping. So given these two values, R and omega naught are known. Given this, you can multiply those two. This you call it a G1, and this you call it G2. Z minus Z minus G1 into G minus G2. Expand it, you will get a polynomial. And this is where A1 and A2 are related to R and omega. That's the logic here. So once you get the HZ, now you can evaluate this on Z. You can substitute G is equal to J omega and take the magnitude part of it. You will get something like this. Phase part of it, you will get some. Don't worry. Focus more on the phase, because it is much more difficult to plot, and also. But what is important, take negative derivative of phase, you will get something like this, except that these values are sharp. This is called group delay. You see? So now, first of all, you don't get confused, why is it group delay? And yesterday I told you That e to the power of j omega t, if j omega t you call it as a phase term, or in general e to the power of theta omega comma t, function of omega and t, derivative of that with respect to omega will be delayed. Derivative of that with respect to time will be the instantaneous frequency. So I am taking the derivative of that with respect to phase, with respect to omega in this case, I am getting this part. See? So now this is my h omega. What about h in n? How do you get hn? Hn, you have this a1, a2, and my b0 is 1, let us say, and b all other b's are 0. Then what happens? Go back to your difference equation and substitute those a1, a2 values, and b0 is 1, let us say, and xn is delta n. So all other bk's are 0. Now that's a recursive relation, you can compute yn. So if you get that yn, this is how it will look like. This is my y. I'm not writing it well, but you can just see. This is my hn, this is my hn. So not very well written, but anyway. So this is my hn. So what it means is, it looks like a damped sinusoid. And what is the frequency? Notice that all the zero crossings occur at regular intervals. That means the one cycle of this represents one sinusoid, but it is damped. So that's why it's a damped sinusoid. So, and what is that cycle when here? That is this omega naught. This omega naught is the cycle, and the damping is due to the R, and which is reflected due to this bandwidth here. You see, I suppose this much. So Hn, given frequency and damping, that is bandwidth, from which I can get R. I will give that expression later. Then I can, given the frequency and bandwidth, I can get these two roots here, or two poles, and from that I can construct the system function, and from system function I can evaluate and construct h omega. H omega is only special case of HD. So construct it and take the magnitude of this, phase of this, take the derivative of this phase, and in the difference equation give those a1 and a2 values, and then give xn is equal to delta n, and generate yn. It will look like this. That is called the unit sample response of the system. And this goes on. This is infinity. You see, it will never stop. Okay. Now, I suppose, tell me before I proceed further, I want to know whether everybody understood this. Anybody has any questions on this? This is the equivalent representation. That means, given the roots, I can get system function. Given the system function, I can get frequency response and also phase response. Given the system function again, I can get hn and so on. So all representations I can derive, or from once you look, give the location of the roots. So in this case, I am considering roots only in the denominator. Numerator I am not considering. That means there are no zeros, only pole, that to pole pair. Is that clear to all of you? So we are going to expand the scope of this. So it is just a damped. Now you can see what I am going to do is the following. You see, if anybody has any questions, you please ask. Ganesh?
Yes, sir. Sir, can you explain the flow once again, sir? From how did you get the h of n? Just the high level picture.
I will do. Good point. First, you should follow this, because rest of it will be very, very smooth there. You see, yes. First of all, what it means is, suppose I want to represent a resonant system. Yes. A resonant system means a frequency and bandwidth. How to relate that will go, I'll tell you later. Let us say 1000 hertz frequency and 100 hertz bandwidth. I want. From that, once you give, I can get R and omega naught. Omega naught is nothing but 2 pi by that frequency. And R can be related to that. I will give you that expression presently. So R and W naught you can get once you give frequency and bandwidth, that representing a resonance. So from that, once you are given that, that means you know the location of the complex locations here, Z1 and Z2. So once you have the Z1 and Z2, write Z minus Z1 into Z minus Z2, expand that, you will get this A1, A2, quadratic expression and so on, because the complex conjugator. So given the location of the root, given the resonance frequency and bandwidth, you will get the location of the root. Given the roots, you can get A1, A2 and HZ. Now, once you get this A1, A2, notice that my B0 is 1, all other B's are 0. So given the, now you go back to the difference equation that we discussed in the morning. This is the difference equation I'm talking about. This is my difference equation. In this, all B's are 0 except B0. And I am making B0 as 1. It doesn't matter, it's only a scale factor. You see? And so it is a, so B0 into, since all K's are 0, you will have only Xn. So B0 into Xn, and this one A1, A2, that's all, nothing else. A1, A2 you have. So A1 is known, A2 is known, B0 is 1, and Xn. So you, to get the, then if Xn is equal to H delta n, put Xn is equal to delta n, that means unit sample sequence. You see? And then you compute this yn for all n. Because the recursive one, only for n is equal to 0, that this Xn will be 1. For all other values of n, this quantity will be 0. Second one.
Yes, sir.
Only this one will be there because the previous one you use and keep on doing this recursion. And this recursion, it goes on for infinity. You see? That is the HF. Do you get it? Can it?
Yes, sir. Yes, sir. So basically, we are trying to get system response, H of n.
That unit sample response of the system.
Yeah, unit sample response, H of n. So,
That is what I have sketched here.
Yes, yes. Yeah, I just wanted the flow. How did you connect that one with the system response? So just the X of n you have done with the unit sample.
X of n is delta n and then compute it.
Yeah.
Is that clear?
Okay, sir. Yes, sir. Sir, and you mentioned about the envelope, right? The H of n. You traced.
No,
right?
no, I didn't say. No, all I'm trying to say, I will come to that. Just hold on for a second.
Okay.
No, what I'm saying is, this is not a sinusoid, but damped sinusoid.
Yeah.
What do you say that? If you take some positive zero crossings here, the spacing, it will be exactly same. That means each cycle period is exactly same, zero crossing.
Okay.
That is the sinusoid part of it. Okay. The damped means the sinusoid amplitude is dying. You see?
Okay.
And the sinusoid amplitude is dying because of this R. You see?
Yes.
I'll tell you what. So that is also equivalently representing this width of the resonance. You will see presently what I am going to do. Okay, that will make it clear.
Sir, one question, sir. One last question. You mentioned the zero crossing, right, sir?
So zero crossing, yes.
Yeah, zero crossing. The width of the zero crossing is equal throughout the signal, right?
Exactly. You see, now I will just show you what it's. Maybe this will be clearer. Then I just my hand is not going properly, but you should imagine that I am writing a sinusoid.
Okay, sir.
Okay. It is a sinusoid with time.
Yes.
You see, you are sure. So, what is the property of sinusoid? This zero crossing and this zero crossing and this zero crossing. Okay, this period will be exactly same, isn't it?
Yes, definitely.
That is the period of the sinusoid.
Yes.
And 1 by that will be the frequency.
Yes.
You got it?
Yes, sir.
That is exact. Now, the same sinusoid, it is a pure sinusoid. There is no decay. Same sinusoid, if I now write like this, without disturbing the zero crossings.
Okay.
Okay. Now what is happening? My amplitude is decaying.
Yes.
You got it?
Yes, sir.
So that is what I have sketched here.
Yeah.
Is that clear?
Yes, sir. Yes, sir.
That decay is due to the location of this root.
Yeah.
R. And that in turn is reflected as a bandwidth here. This is the resonance frequency of omega naught, this is the bandwidth. So both are related to that R and omega naught. Okay. Now,
yes,
just to see what I mean, it will be very clear now. What I will do, if you have to follow my pen here. So I just push this R to some location here and slightly greater than, let us call this as R1. R1. All of you can see my dots?
Yes, sir.
Yes, sir.
So my R1, let us consider a case where R1, which is greater than R. R1, which is greater than R. Okay. Now, please follow this carefully. Now let us go through all these steps. Once the omega is same, omega naught is same. So this R1 is greater means what? it is closer to the unit circle. Closer to the unit circle compared to R. So now for that, you recompute A1 and A2. Okay? I suppose you know how to, omega naught is fixed. And then you will get Hj and for that H omega comes. How does it look like? Just please watch my, see, I have to plot it on the same thing for us to see the contrast. I will try to do with pencil here on this. Please follow this carefully, what I am doing here. So this is how it will look like. Ganesh, can you see this pencil curve?
Yes, sir. Yes, sir. We could trace it.
Yeah. So what do you see the difference? This difference is the location of the peak is same.
Yes.
But the width of the peak is different.
Yes, yes.
And the width is narrowed now.
Yes.
If it is narrowed down, the corresponding Hn will be, if I plot it on that, you can't see it clearly. But so I will do it try to do it as carefully as I can. And so this is what you will get.
Damping will reduce.
Yes.
Damping will be less. You follow what I'm saying?
Yes, sir.
This is sharper, so damping will be less. Zero crossings will remain same. Is that clear?
Okay. Yes.
Now I will move further. I will move further the dot right under the unit circle. I don't know whether you can see that. If it is right on the unit circle, then what happens is, you will see, in fact, you should do this experiment in the MATLAB. What you will get here is the following. I think I am exhausted of the colors and so on. So, or you have to see, you follow this one. So it's in fact exact means slightly small delta x less, otherwise, so it will be almost like a straight line. Ideally, if it is on the unit circle, this goes up to infinity. You see, so but it is, of course, there are other points here, so it is very large. That's where it becomes what is called an ideal sinusoid. It will go like this. The amplitude don't change, but zero crossings also don't. Is that clear to all of you? So this is when I put the root on the unit circle. Is that clear? That means damping is zero.
Yeah.
Now I don't stop here. I don't stop here. I now move the root beyond this. That means now my root is here. Okay. So what do you expect? What you expect is the following. You see, again you have to follow my hand. This one, you see. So what I expect is just to. So this will. I have to put a smaller amplitude here to
expand.
What are you seeing here? This is called a growing sinusoid. You follow what I'm saying?
Yes, sir.
Zero crossings remain same. Now it is not damping, but it is growing sinusoid. This happens when the system is unstable. You see?
Yes.
So, but doesn't matter. I didn't talk about stability, so that word itself will be difficult. So, but as you keep moving the root outside the unit circle, this is what happens. Inside the unit circle, damping, outside the unit circle, growing. On the unit circle, it is a pure sinusoid. And you can easily imagine the corresponding phase and other things. I am not going to show that. You see? Is that clear to all of you?
Yes.
Any questions on this? Once you follow this, rest of the thing what I am going to say will be very easy to follow. Now what I will do, if you have any questions on this, please ask me. So all I have changed, omega naught I have fixed, but I am only changing R. So if you go towards the origin, let's say, if R is less than, let's say R2 is less than R, what happens then? Damping will be more, zero crossings will remain same, and this gets broader. So you can easily imagine, that's not a, is that clear? Now next question. Instead of changing R, keep R fixed and change omega. So instead of omega naught here, you keep this R same. This is the same R. I suppose you can follow my pencil. And so this is my new omega naught. This is my omega naught here, minus omega naught. R has not changed. All right. So what do you expect? What do you expect? Can anybody see what you expect? All that will happen here is, you see, I cannot unfortunately plot on this because it gets messy already. So what I am trying to do is, I will take some omega 1, which is greater than omega naught. Let us say this is my omega 1, this is my omega 1, and which is greater, R being same, you see. So now it is R e to the power of plus minus j omega 1. You see, that's what I have. See? That is the, where omega 1 is greater, what will happen now? So in the case of first, this one, this is omega, this is this one, this is pi and minus pi. Very simple. Don't struggle too much on this. All that you have to do is, see, maximum you can go omega is up to pi, because pi is the half the sampling frequency, you see. So, and so maximum you can go. Now what happened? Earlier my omega naught was here. Now this is my omega 1. And this is my omega ns omega naught. This is my minus omega 1. So all that happens now is this one. Do you see the difference? What happened here is the peak got shifted to omega 1. Correct? Any questions? So now you can now see all the rest you can easily follow, but let me write the Hn. Hn for this. This is N, Hn. Can anybody, before I plot this, let me see how we can maintain. Can anybody guess what change will happen in Hn?
So zero cross count will change. I mean, would vary.
Excellent. So the zero crossing spacing will be reduced. You see, reduced means you will have something like this. Compared to this, that means if you see, take the zero crossings here, this T1, this will be less than this T. Get the point I'm saying? Why? So what is this T1? T1 is nothing but 1 by omega 1 or 1 by F1. So because F1 has increased, T1 decreases. So this shows higher frequency. Very simple. The rest of the things are all same. As you keep now making this route moving along the R, you can see more damping, less damping, and so on. Any questions on this? I hope you understand this. Now let us move to other. Now the beauty of this is, please note this, very important. Suppose my R omega naught is such that the root is not on this, but root is right on the let us say in this, the root is right on the unit circle. Sorry, on the real axis. This is my R, my omega is 0 here. Suppose this is the case. So if the complex conjugate, both roots met here. So there's no problem. Suppose this is the rule. Now what happens here? Now what happens is, the frequency response, if you see, mod h omega, can everybody guess how it looks like? When omega is 0 now, omega naught is 0, what will happen? This HO. Anyway, I will, to save time, I will write like this. The whole thing will be no problem. The resonance, you can also imagine, resonance frequency got shifted to 0. That's all that happened. Instead of omega naught, it gets, since there are two are there, both of them merge at origin. That's what it is. You see, this is what it is. Follow what I'm saying? So basically, this is for a, and now for the HR on this. Anybody? Can you see what happens for HR? Anyway, to save time, I have to do just, it's simply a decaying curve. There is no oscillation here because it is 0 frequency. So this is the thing. So Now you can also, let us also go to the other part where instead of on this side of this omega is equal to fs by 2 of the sampling frequency, let us say, then what happens? Then what happens? This is minus pi, this is plus pi, let us say, and if you have the roots on the real, this is what will happen. You see, this is minus pi plus pi, this is how it is. And also because it is periodic, it goes like this forever. So that means that peak will be at pi or minus pi. That's what. And of course, can you guess what it is before I close? Can you guess what Hn will be like for this case? For this case, kind of a thing?
Growing exponential.
Beg your pardon?
Growing exponential.
No. For this case, what will happen?
Only one frequency component might be there.
I want to hear some more. Yes, sir. What will happen? It's a very, you see, I think, of course, you just see from this omega to omega 1, what happened? The cycles have increased, isn't it? Correct? And so when you are taking all the way up to fs by 2, what happens? It will be simply again decay standard, but it will be at a sampling frequency. So this frequency is the highest that you can get. You understand my point? Because my peak is at fs by 2. This is how maximum frequency, half the sampling frequency, isn't it? And that is where you have the peak. Decay being same. So decay is same, but this is the frequency cycles will be maximum. Is that clear? Let me ask. I can see Ganesh name here. So Ganesh,
Yes, sir.
is that
Yes, sir.
clear?
Yeah, it's clear.
So if you are able to follow this, you see, I mean, you please practice a little bit. Very, very simple. You see, but a lot of people jump this and they don't want to learn. But you know, once you learn this, it's very now now what happens is, let us say, I am not going to spend so much time anymore because you understood already. Suppose I have not one, I have two of them. Suppose I have two of them. All that it simply means is I have the resonances like this. This one. Okay. Minus pi plus. Because there are two resonances. Now you can have three resonances and so on, like that. Anyway, I am not going. Is that clear to all of you? So the reason for this is now, given the resonance frequency and bandwidth, I can get R and omega. And given the R and omega complex, I can construct the polynomial, second order polynomial. Given any number of pairs like that, I can construct that many second order polynomial and then multiply all of them. Then you will get a single polynomial of a higher order. That's exactly, that will be your A1, A2, A3, etc. You see? And follow this. It doesn't matter how many. So why do you need this now? Suppose I want to construct R. So generate a system to produce R. All that you have to do is find out the three resonance frequencies or four resonance frequencies. Let us say F1 is equal to some 700 hertz, F2 is equal to some 1200 hertz, F3 is equal to 2500 hertz, at 10 kilohertz and so on. Once and also give the bandwidth, let us say 10% bandwidth or something. You can get those three frequencies, corresponding locations here, and get the HZ, that means A1's AK is there, and use the difference equation, produce that, listen to it. It will sound like R. You follow what I'm saying? On the other hand, if you say E, obviously the first resonance frequency will be around 300 or something, second will be around 1100 or something, third will be like this. So you use those locations and damping, and then generate the signal, you will sound, it sounds like E. So now you understand why this representation is needed. Okay, I suppose it is clear. And now let us move forward and just close this part of it. So all along I am considering roots only on the what is that denominator polynomial. Why not, like, if I consider roots in the numerator polynomial, there will be zero. Suppose I have two zeros like this. So that means this is it will give A1, B1, B2, but it is the numerator polynomial. You see? So then what will be its frequency response here? This is my omega. This is omega here. This is minus pi. This is pi. Okay. And this is my omega naught here, minus omega naught here. And this is my omega naught, let us say. And this is my R. Okay. So how does it look like? Anyway, you can later verify this. I just want to, I'll just this is what you get. That is, there will be null here, and this is not a peak. This peak is coming because of the shape of, because null is placed here. You see, that is the point. This is not due to pole, but this is two zeros at complex conjugate location. So that means it is exactly in the log domain. If you take exactly minus of the magnitude log h omega for pole will be exact log for zeros. It will be exactly minus of that, inverse of that. So that is not difficult to follow. But what is difficult to understand, I would like to hear from some of you. What is Hn here? Anybody? What is Hn here? Notice in this case, all A's are 0. All A's are 0. I don't have only B0, B1, B2 are there. So what will be this response? Any quick response, right or wrong?
Also similar to what we observed there, but starting from 0?
No. You have to think. Notice, go to the difference equation. The first part, A's are all 0. So the recursive part has vanished. You see? I suppose you understand what I'm saying. You see? If you, the recursive part has vanished. Can you see the difference equation? In this AKs are 0, so this part doesn't exist. Only this one exists. B0, B1, B2 are there. That's all. And Yn. So what happens? Notice that when you put xn is equal to delta n, you will get only 3 numbers. B0, B1, B2 is all the response Hn. There is nothing else. Because beyond 3, beyond 0, 1, 2, beyond n is equal to 2, that is 3, 4, and so on, the values are 0. So that is why this is called a finite impulse response system, FIR. Whereas the moment any one of these A's are not 0, then it becomes infinite impulse response. So the response for this will be only 3 points. There will be some value here, and this is my B1, and this may be my B2. That's all. The rest of them are all 0. That is the response. You got it? So, I'm sure if I were facing you, I would have seen a question mark face on your face, but now I can't see you. Do you follow anybody want to respond? Do you understand this?
So can you repeat it once again?
Yes. First, do you understand the problem? In the G plane unit circle, I am putting in the pole, I am putting a pair of zeros. Correct? So I will get a polynomial. In this case, B1, B2, I will get not A1, A2. All right. So it will be numerator polynomial. That means Hz will be 1 plus B1 G minus 1 plus B2 G minus 2. This is the polynomial. This is what I get. And now, of course, if I write G is equal to J omega, this is what I get response. This is my mod H omega. Okay. On the other hand, if I want to get Hn, go to the difference equation that I have. Go to the difference equation I have. Ignore this part because all A's are 0. And put xn is equal to delta n and try to get Yn. So you will have values y0, y1, y2. And you can see y3, y4, y5, all of them will be 0. You can try that. So that means the response stops once the B stop. You see? So that is why the output will be 1, B1, B2 is the response. Is that clear?
Yes.
Yeah. So this is it. So now you can have a pole zero combination as well. So if you want to design a system which has this many resonances, this many anti-resonances, this is the way to go. Okay. So this is what is called the equivalent representation of signals and systems. Okay. And I think I would like you to spend at least half an hour tonight to go over this once again, because it is there in many books, but it is spread out all over, and maybe in between they will give some examples, some programs, it will distract the attention. But if you get this total picture, very simple, and program is simply trivial, because MATLAB gives built-in program, but if you write a C code or something, there's only two statements. Now, before I close the discussion on this, I want to give you a, suppose you define, let us say sampling frequency Fs, Fs is equal to 10 kilohertz, and I have resonances, let us say F1 is equal to maybe 1000 hertz, and F2 is equal to, let us say 2500 hertz, and so on. Let us just take over. And B1 bandwidth is equal to, let's say 100 hertz, and B2 bandwidth for the resonance 250 hertz, just for the sake. So now how do I get the system function for this? I will give you the expression, but you have to figure out later, because we don't have time to do that. And so my HZ for this will be like this. My A1, A2, I'm going to write here 1 minus twice e to the power of minus pi B1 BT, okay, cos 2 pi FT z minus 1 cos 2 pi FT plus e to the power of minus 2 pi BT g minus 2. So my A1 will be minus of 2 e to the power of minus pi BT cos 2 pi FT, and A2 will be simply e to the power of minus 2 pi BT. You may say, how did I get it? It's very simple, but it takes another 10 minutes to explain. So I don't want to do that. So given this, you can get A1, A2, A3, you or e to the power of the and then do this kind of thing. Given is A1 in terms of F and B, A2 in terms of B. So for F1, you get one A1, A2. For F2, you get another A1, A2. Two quadratics you get. Multiply those quadratics, you will get a fourth order polynomial. That will be the HZ. And for that, if you can get Hn and so on, you will get the response, which is captures both the resonance and so on. You see. Now, this is what is, suppose this is my system. This is my system here, okay, and represented by this Hz, okay. Instead of giving one impulse, what I want you to do is take, let us say, an impulses at the spacing of 100 samples. This is 200. This is my n. So there is a unit. This is delta n minus. You may want to use the m into 100. So what it means is n is equal to 0, you have m is equal to 0, m is equal to 1, m is equal to 2, like this. These are the unit impulses here. So you keep doing this and use this Hz, generate this, you will get what is called something like this. And I want you to write a simple MATLAB program for this and generate this and listen to that. listen to that. It will sound like speech. Depending on this, and this particular one is called the fundamental frequency. Instead of 100, you make it 50. Instead of sounding like ah, it will sound like ah, like that. Higher pitch. That means smaller interval and so on. So just a simple program like this and produce this. And of course, you have to produce hundreds of cycles, maybe corresponding to about 10, 5, 6 seconds or something. Because very short you cannot see. So this, because 100 samples simply means only 10 milliseconds. So you need to produce 2-3 seconds of speed for you to pursue that. So you will get something like this and listen to it. Do this experiment, having listened to the last 3-4 classes from me. You do this experiment for yourself. You can see the significance of what we discussed until now. You see, otherwise you will say, why are you boring us with these transform, Fourier transform, system function? What is all this going on? Impulse response is all, you may think it's all waste of time, but all that is only to understand this process. You see, only to generate. So I will move to the next topic, but before that I will pause and ask any questions.
So can you please explain this assignment once again, this exercise?
Can you repeat, please?
Can you please explain this exercise once again, the MATLAB code, what we have to do exactly?
Your voice is big. Can I repeat? You asked me to explain what you have to do. Is that right?
Yes, sir. Yes, sir. What do you expect us to do?
I will do that. I will tell you. So if you had followed what I have discussed until now, that equivalent representation, I want you to implement it for a practical speech signal, synthetic speech signal. In order to do that, assume a sampling frequency of 10 kilohertz. That means sampling interval will be 100 microseconds. You have to put some specific values here, you see. So capital T will be 100 microseconds. So then you have, let us say, design a system which has a resonance frequency of 100 and the band of 10% of that, let us say 100 hertz. 1000 and is the resonance frequency, bandwidth is 10% of that. Likewise, resonance frequency at 2500 and the bandwidth is 250. You see, this may not sound like any particular vowel. I'm just giving some random vowel, but later it will be nice when we come to further analysis, which we discuss tomorrow and after. You can try this for your own voice. You will derive from the speech signal the and plug into the resonance frequencies back here and synthesize and your own voice. That's what I want to do. So first, this is only to experiment the basics of DSP. So what I am suggesting here is, given the for resonance frequency, here I have given 2 resonance frequencies and corresponding bandwidth. And instead of troubling you, I am giving directly once this is from this R omega can be obtained very easily. So once you get R1 omega 1, R2 omega 2, if you get using that G minus G1 and G minus 2 product and so on, you will get A1, A2. I have directly given you the expression for A1, A2. It's very easy to derive, but it takes a little time to do it. So where my capital T will be 1 by S, the capital T is equal to 1 by Fs, you see. These are all numerical values, you see. And so the F will be the frequency in hertz. So frequency and time multiplied, it will be dimensionless quantity. So substitute them. F1, B1 here, you will get A1. F2, B2 here, you will get, F1, B1 in this, you will get A2. And likewise for F2, B2, so you will get one A1, A2 twice. That means one A1, A2 for this, another A1, A2 for this. Multiply these two quadratics, you will get fourth order polynomial. And that fourth order polynomial with 4 coefficients here that you have, use that in a difference equation. And where b's are all 0 except b0, b0 make it 1. And make xn as xn. Normally earlier I said to get hn I need delta n. Now one delta n is not enough because you will get only one damped sinusoid. So it is too far. You don't have enough time to listen to it. So what you do is sustain it. That means give one impulse here, another one unit sample here, another unit sample after 100, another unit sample after 200, and so on, and keep doing it for about 100 or such cases. So generate roughly, you can calculate roughly for about 5 seconds of duration this one. Now use a MATLAB program for which you can, there is a program called frequent, you can ask the expert there. So there is a program called where it gives the numerator and denominator polynomials, the coefficients you have to give, this input you have to give, you will get the output straight away. You see, so you don't have to do anything. Once you get those coefficients and generate this HZ, you plug in and one command, it will produce this. That's what I want you to do. You produce this and listen to it. See? And to listen to that, you need to produce these symbols at least for about 100 or 1000 of them at all, because then there will be enough duration to see. Then what you want to do is you play with these F's and B's. I only gave 2. You can also put 3, F3, B3 also if you want, but only for these 2. Change the frequency, change the period. Instead of 100, make it 150 or 50, something like that, and play with that and see how it sounds like. That is called a synthetic signal. You see, and that becomes a synthetic speech if you give F1, F2, and so on corresponding to some sounds like some vowel sounds and so on. Then it becomes a synthetic vowel and so on. So that is what I want you to do. Right now you are plugging in these values randomly, but later you can plug in the value corresponding to your own speech. You can do that experiment, do the analysis which we are going to discuss in the remaining classes, get those F1, F2, F3, and generate, design a synthetic system and produce the synthetic signal. Is that clear?
Yes, sir, it's clear. Thank you, sir.
So all of you, please do this. Don't ignore this instruction, because all the effort of my putting the effort to talk to you and you're putting the effort in listening to this will go waste if you just listen and drop it. You see? But you just do this, it will stick to you for the rest of your life. You see? So you know what is happening. You see? And this forms the basis for all signal processing in general, speech signal processing in particular. You see? Is that clear? Shall we move to the next one, or anybody else has any questions to ask? No? Okay. I am assuming that you also. Let us move to the next topic. Now we have built the basics of the, of course, obviously we cannot cover too much, but we have covered some basics. Now the rest of them are all simply some more properties of DFT, more properties of all linear systems and all that will be there, but you will pick up as and when it's required. You don't have to. If you understand this thoroughly, you can do a lot of things. And the next topic what we will study is what is called the introduction to random process. You may say, suddenly you are talked about DSP and so on, why are you switching to random process? Unfortunately, we already mentioned briefly in the first day's lecture, but now we will elaborate why random process concepts are needed to do and also understand speech signal processing. Okay? And without that, you cannot understand many things. We loosely use the word frequency, we loosely use the word spectrum, and so on. So what we get used as spectrum is not spectrum. You see? What we use as a frequency is not a frequency. You see, that is the problem. You see, so as people who went through this program, a regular program of speech, both for speech as well as hearing, you should know what to, although when you give a talk or something, discuss with others, it is implied they also know this. Otherwise, when you talk, you should know internally at least that these are only a term that are used, but they don't convey the precise meaning. There's no concept of frequency at all in speech. There's no concept of spectrum at all in speech. All that is only, that is why you need random process idea to clarify some of these concepts. So that is what we thought we will discuss. Some background of random process. It looks like, I don't know. Can anybody, Jagbandhu, can you tell me how long I can go? It's already 3:35. Otherwise, I will pick it up tomorrow. That's what I'm trying to say.
I think it will be better you can do it tomorrow, sir.
I think so, because already this is loaded. That will be a little more load and conceptual load. And also whatever
Yeah.
I say now, I'll have to repeat also tomorrow. You see. But unfortunately,
Yes,
that
sir.
gives me almost 1.5 classes lag, but it's okay. I think because my worry, not my worry, my objective of this program is because some people from different discipline, different backgrounds also maybe share relevant background as well. They may not have the picture, complete picture of what is going on in speech signal processing. Maybe they have bits and pieces, some coefficients, how to extract and so on. So, but more than anything else, I want you to understand this.
Stop. Hello.
Hello.
Yeah, Ayush.
Yes, shall I start or we will give a 5-minute break?
Yeah, we'll take 5-minute break, then start. So
Start for
it's
like
3:33. So we'll start from 3:40.
Okay.
Okay, now it is. Hello? I suppose, can you hear me? Power went off here. So I think asking us to close, but I want to just, before I close, I want to hear if anyone wants to ask something. I will not start the next topic, which I will do it tomorrow morning. Okay? Tomorrow afternoon. Anybody wants to ask anything? Anything. General, doesn't matter pertaining to this kind of even other topics? No? Now it is okay. Okay. Yeah, I suppose all of you can hear me because some problem with the operation here. They didn't allow me to unmute. So maybe you may not have heard what I said a few minutes ago. My question is maybe next topic I will start tomorrow morning. And although I may have to compress the remaining topic, but I think whatever I have discussed so far is probably very important background. And I would like all of you to pay attention to this. And right now, if any of you have any questions to ask, please say so. Your question, comments, anything that you want to say, please do that. Otherwise, we will close in a few minutes. I suppose all of you people are listening to me.
Yes, sir. We are listening.
Good. Okay.
If you have any questions, can ask the professor or else.
I think I don't hear anybody saying anything. I can wait for a couple minutes or so, no problem. All of them are in a mood to break. Okay, if Jagabandhu, what do we do? Shall we close?
Yes, sir. We can close and can.
No, I'm just saying. Or you want me
Yes,
to
sir. We
wait
can
for
close. You can start the tutorial sessions. Maybe actually I have given a break actually at 3:30. That told that 3:40 will start. Maybe we'll wait for some time. That is why some people maybe go out for the
I have
break.
no problem.
So 3:40 will check once if there have any doubt, then or else maybe we'll take the doubts even tomorrow.
Yeah.
And we'll start the tutorial sessions now.
Right. Yeah. Sure.
We'll wait for 2-3 minutes, sir. We'll see.
Beg your pardon?
Well, wait for 2-3 minutes, sir.
We'll wait. No problem. No problem. And also, what I notice is, I think the interest is slowly dwindling. Even all the program, I think they have to maybe from our side there is something which we can correct. We can do that. There's no problem. But it is a general decline. There's nothing we can do. No. I mean, at least those who are present, I hope they will take benefit of these all these lectures.
Yes.
Yeah, normally, yes.
Yeah. Have any queries? Can
Somebody
ask.
is asking something, or sure.
Okay, let me check the chat box then.
Type message here. Okay.
Is there any noise other than white? Someone is asking, is there any noise
Somebody
other
is
than white
asking,
noise?
is there any noise other than white noise? There is only noise, only white noise doesn't exist. Okay. Yeah, it's a very good question. Lot of us get so much of misconception here. but white noise doesn't exist. Everything else is a noise other than white noise. Okay? And since you raised this question, I will see if I can squeeze in some time tomorrow to explain that. White noise is a concept from random process, you see, and so in reality it doesn't exist at all. Okay? It is only an approximation. I will show you, and in fact, in digital domain and discrete time domain, the concept of white noise simply fails, although we still use it. Whatever we use it is such a crude approximation to that. And of course, I have many things like that to highlight, but I will see tomorrow. Anything like that, if I do, it will take another 5-10 minutes. But since you asked this question, I would like to clarify about noise tomorrow. Okay. And please wait till tomorrow because it requires the idea or a concept of random process, which I think some of you or many of you may have it, but you may not have heard me saying about it. So you hear from me first, and then I will also discuss this noise business in the process. Okay. But you can take it from me. Your question is there any noise other than white noise? There is only, except white noise, every other noise exists. White noise only doesn't exist. Okay. And I will highlight this point when I come back. Okay. Same thing with Gaussian distribution, white noise, anything you take, all these are simply some ideal situations, which in fact, when you start putting it in practical, this one, there is a fallacy. One can argue for and against it, and a person like me will argue against it. You see, because it neither reflects a ideal noise nor it reflects a practical degradation situation. We are neither here nor there, but we still keep on using, noise database and plugin and so on, get numbered. I mean, it's all crazy thing, but you can't help it. Everybody is doing, so you also have to do it. Otherwise, that is simply not the way to do. Okay. Anytime you want to work in speech, especially, I think your question also is related, indirectly probably related to practical speech, where there is a degradation. That is a very important thing. You see, now speech cannot be collected or obtained without degradation. And the degradation you want to call it noise is up to you, but it is not noise. It is simply degradation, which is not what you want, speech that you want. So the fundamental problem that people should pose, and also although they use this speech enhancement, but most of the papers that I read or discussions I see, they are not worried about speech. They are only worried about the degradation and try to suppress it. That is wrong. You should try to enhance speech. To enhance speech, you should know what is speech. What are the speech characteristics, and then enhance it. That is what you have to do. But unfortunately, the whole literature is mixed up, and researchers are mixed up, and everybody writes all kinds of nonsense here. They are absolutely trash. That's why you need to know so much about speech. You need to know so much about speech so that you pick what you want rather than keep worrying about the disturbing part of it. You see, that is the beauty of it. That is the reason why speech processing is needed. Okay. All right. We will hopefully discuss some of this as comments in the coming few lectures. But I think I have only 4 more lectures to go. I will try my best to do this. We have to discuss quite a few speech processing. But I will, if I don't cover this part you are mentioning, please raise it again. Okay, that is then only quite possible that I may forget. But it's a good question you asked. This white noise, pink noise, this noise, all these are useless terms. They have no scientific relevance at all. Those are all useful for writing some papers because they want some way to compare it all. You have to really talk about speech and speech enhancement and degradation. Speech, what is common is speech. What is required is speech. And what is not common, what is varying is degradation. What is, see, the environment, suppose I am talking in this room, tomorrow I talk this, I give the same talk in some other room, the environment is different. My speech will be similar. So what is common is speech, and the challenge for speech signal processing research is how to pull out the speech, understand and pull out the speech characteristic rather than worrying about the degradation. Because no degradation will be same, identical, stationary, then none of the properties work. And no degradation is mathematically model. You cannot model any degradation by model, like white noise, pink noise, and so on. All these are, terms that are used very casually, and that is why any system that you build in the with these model noises, in practice, most of them don't work at all. See? And of course, they quote some numbers, performance numbers, and so on, but all those are, goodness, some. What is that? Mean opinion scores and all that. That's all fine. Those quantitative figures have no meaning at all for real data. Real data, first of all, speech understanding, of course, as Healy said, then comes if you are a human being and you want to get the meaning or characteristic out of this, you also need to understand perception part of it. Which part is important for perception, which is not. That's all, in the speech context. But all the degradation part you should just ignore. Ignore means you should focus on the speech characteristics, see which can be highlighted. If you cannot highlight, then give up. That's all. There's nothing. Okay. We will discuss this. Hopefully, I will get some time to do that, or I will make some time available. Okay. Any other question, comment? Okay, I think if there is none, we are already going to 4 next. Jagabandhu, I think we should.
Yes, sir.
Because
yes,
we
sir,
have the next program also. So
yes.
Shall I leave now or shall I close
yes,
now?
Sir. Yes, sir. You can close now. Ayush will present for the tutorial.
So I will close. Wish you all. I
Yes,
will meet tomorrow. Okay.
Yes, sir. Thank you.
Okay. Bye.
Okay, thank you, sir.
Ayush, you can present
Yes,
your
yes.
screen.
I will present.
Yeah, please.
So hope my screen is visible. Hello.
Yes, sir.
Okay. So welcome everyone to the third day of the tutorial. So today we will be discussing about the short-term features. So the topics that will be covered will be how to read the speech file and plot the speech file in MATLAB. And now just will give a broader view of the window. So the topics will be like how do we read the speech file and how do we plot the speech file in MATLAB. And then we will be discussing about the non-stationary nature of the speech in both time and frequency domain. So that will be the motivation, like how it looks in time domain and frequency domain. Further, motivated from the non-stationary nature, we will see the short-term processing. So there are two short-term processing. One is in time domain. Again, the other one is in frequency domain. So in time domain, we will be covering short-term energy, short-term zero crossing rate, and with the help of short-term energy and zero crossing rate, how can we detect voiced and unvoiced speech? In short-term frequency domain processing, we will be seeing wide and narrow band spectrograms. So let's start. So say we have this speech file in the dot wave extension and we have to read it. So audio read is the command that is used to read the speech file. Okay, any question? Someone's talking, I guess. Okay, fine. So here we are storing it in a variable s, and s is the sample frequency. So the so audio read takes the speech wave file as the input and gives a speech file and the sampling frequency as the output. So here, okay, let me run this part. Okay, fine. So fs, the currently after reading the audio file, we are getting the sampling frequency as 8 kilohertz. We can calculate the duration also. So how do we calculate the duration? We count the number of samples that are present in the speech file, divide by the sampling frequency. So in that way, we get the duration here, 3.5925. And for plotting, it's simple, like we just use the plot command. There's an inbuilt command in MATLAB. With respect to the time, we will plot the, like with respect to this independent variable, we'll plot this dependent variable, that is the speech. So let's look at the speech waveform now. So you know that speech is a very continuous signal, but it is actually, for when you process it on machines, it's not it's not a continuous signal. We process it in samples, right? We cannot process directly a continuous signal. We have to convert it into a digital signal by A to T converter, and then we have to process it. So if you but when you see this waveform, you will be seeing that, okay, this is continuous waveform. How is it digital in that form? So actually here we have samples. MATLAB plots it in the continuous wave. But if you see now here, so we have this quantized in the in the y-axis and discretized in x-axis. So in this way, actually it's samples only. So let's see this part. So how is it samples? So you can see here. So this is the first sample. This is second sample. So actually this is a stream of samples only. It's not continuous signal. Therefore, whatever processing has been done, it's in the digital part. So let's move forward. So for this coding session, I have taken a small segment of the speech of 50 millisecond. Sorry, a 0.5 second, and then we will be using this segment for our processing part. So I just sampled, like taken a small segment. How do we take that? I take the first sample, and here colon means like first sample to the sample you want to capture. So I will be taking 0.5 or the total or the sample frequency. So this will be giving me 4K samples, and I have plotted it with respect to the independent variable here. So this is the waveform. Now let's see the non-stationary demonstration. So again, like we know that speech is a non-stationary signal if we see complete signal as it is, right? If you see this complete signal, we can say that it is non-stationary, but can we give a valid proof for that? So let's see this plot. So these two are the segments of the speech at two different instances of time. So I've taken a 40 millisecond segment from two different instances of this waveform. So when you closely analyze this, so for being a stationary, it should be like throughout the span of time, it should have same shape of the waveform. But if you closely analyze these two, is it the same? It's not, right? Because the shape of the waveform is different in these two. Therefore, we can say that since at different instances of time, the speech is not having the same shape, it is non-stationary. So I've just taken two segments at two different instances of time in this way. Like as I've discussed before, how do we pick a frame of a large speech segment? So this is the way how do we pick that. And here is just the simple plotting part of that we have already discussed in the previous section, how to plot. This is from the time domain. We are motivated from the time domain that speech is non-stationary. Now coming to the frequency domain. So for the same segment of that speech, for this segment, I have taken the DFT, which is like in MATLAB, there's an inbuilt command FFT. It computes the magnitude spectrum of that speech segment. For both of these two speech segment, currently we have taken out this magnitude spectrum and we have plotted it here. So how do we compare whether these, just looking at the frequency spectrum, can we say that whether the speech is that both of the segment of in the time domain belong to the stationary part of the speech or not? How do we say this just after looking at this plot, these two plots? So let's see, if you see this third peak here, So both of the peaks have different amplitude, right? If it would have been the same, if it had been the stationary signal, which means that the time domain the waveform is same, then the frequency domain also should have given the magnitude spectrum same as like same to same, right? But it is not the case here. The third peak has the higher magnitude in compared to the third peak of this segment. Therefore, from both time domain and frequency domain, we can tell that speech is a non-stationary signal. So all the signal processing techniques that we read, like Fourier transform and all, those are mostly for the stationary part of the signal. So can we not apply this transforms on the speech signal? We can. How we can do that is we can split the speech into small parts, like if you like small frames. Within a small frame of around 10 to 40 millisecond, it follows a periodic nature, which means it is stationary. If you see this waveform closely, then the shape of this part is similar to the shape of this part, and similar to the shape of this part, and throughout in this frame. Similarly, in the second segment also, if you see this cycle from here to here, the shape of this part of the cycle is similar to this part of the cycle, right? You can see this one, like the arrow how I am moving. So this is one cycle, and this cycle, second one, this also has a similar shape as the previous one. So therefore, in a frame of 40 millisecond, it is following a stationary nature. Therefore, we can apply various signal processing tools here. So now, since we have seen that we can speech is a non-stationary signal, and to apply signal processing techniques over that, we have to make it like, and in the small frame of for 10 to 40 millisecond, it is behaving as a stationary signal. So we can apply the signal processing tools. So for that, we have to divide it into small frames and do short-term processing over that. So what is basically short-term processing? Short-term processing, as I explained, processing on a small segment of the speech signal in which it is following the periodic properties and all. So that is basically short-term processing. So it is done in two ways. First is short-term time domain processing, and the other one is short-term frequency domain processing. So windowing is a method that is commonly used to segment the speech signal. So we pass the entire speech signal through a window, and basically Windows segments it down into small frames of 10 to 40 millisecond, depending upon the size of the window. So definition is like dividing the speech signal into small frames is called windowing. So generally people use that, like the most famous windows are rectangular window, Hamming window, and Hanning window. So let's see how do we plot, how do we extract that window, how do we like write the code for that. So rectangular window is basically just like, let me show you the figure. Okay, yeah, this figure. So this is a rectangular window, just one throughout the samples, number of samples that we need. So it's completely one. Then we have Hamming window. It's like of this shape, and similarly the Hanning window. So how do we compute that? So in MATLAB, we have the inbuilt code for that, termed as like, if you want to generate the rectangular window, you just specify what length you want at, and then you write just ones L comma 1. So it will generate a array of ones. So that will be basically our rectangular window. Let's run this code. I have to run the previous ones also. This. Okay. So let's see rectangular window first. So you can see all are ones. Like we have specified the length of window as 320, and we are getting all ones up until 1 to 320. So this is how we have designed the how you can design a rectangular window. For hamming, there's inbuilt command of hamming, and just you have to specify what's the length, what length do you want for the window, and similarly for hanning. So now we'll see like what's the benefit of one over the other. Like let's analyze that part. So there's a drawback in rectangular window. The rectangular window is used for segmentation, but the problem there is, if you see this is a rectangular window, right? If you pass the speed signal over this rectangular window, then it will give the abrupt change as at the boundaries, right? Sudden cut will be there at boundaries, so continuity will not be present. Whereas in Hamming window, when you pass the speed signal, so it will smooth it out at the boundary, because like it will not give the abrupt change. Similarly for the Hanning window, the Hamming window is mostly used in speech processing, because if you see the Hanning window closely, it goes to 0 for some of the samples. So at that position we are not passing the signal at all. So this is also not well practiced technique. So Hamming window have a benefit that it smooths it out at the boundary, and also takes care that at boundary the signal speech is not absent, it not gets vanished. So that's why this Hamming window is mostly preferred in speech processing. Now coming to that is we have seen in the time domain for the window. Now coming to the frequency domain, let's analyze what the benefit of one over the other. Yeah. So generally, rectangular window is said to have a spectral leakage. Spectral leakage means if we see in the frequency domain, when we pass the window in the when you pass the speed signal in time domain, there's some effect in the frequency domain also. So here this is the main lobe. We call this as the main lobe, and these are the corresponding side lobes, right? So in rectangular window, the ratio of the peak of the main lobe to the side lobe is quite low, due to which there's too much of leakage here in the spectral domain. So that's why it is not preferred to use rectangular window. Whereas if you see Hamming and Hanning windows, it decays here. So the effect of spectral leakage reduces significantly with respect to the rectangular window. So that is why we prefer Hamming and Hanning window over the rectangular window. Now coming to like we have discussed how do we segment or how do we window a speech signal. Now we will discuss short-term energy. Like now we have come to a frame level. Now we'll compute the energy of every frame. So energy is associated with time. Energy associated with time is time varying in nature, because since speech is also time varying in nature. So we are interested in like how in the short period or short frame, how the behavior of energy is. So with respect to that, we compute a short-term energy. So how do we do that? We first take the speech signal and we do the windowing of that and get a speech at a frame level. Now we square every element, like simply just element wise square, and sum of all those element wise square elements within a frame. So that in that way we compute the energy, right? So let's see how do we do it through coding. So we take the speech signal and we define a Hamming window. Now, so these are just computing the lengths that will be required while doing the framing while doing the frame, like dividing it into small frames. So this is the code that can be used to divide it into a frames. So we define first we have to define an array, like we call it as initialization. So we initialize an array with all the zeros, and the length of that array will be the length of the window, because in that window size only we will be dividing our frames, our speech signal to frames. So we do that and see what all are the indexes of the frames of every frame. So that we will be storing in this index of the frame. And finally, we divide it into different frames here. Now it has, now currently if you see, here we have used rectangular window. So we have divided into frames of rectangular window. Now you will be seeing that I have said before that rectangular window is not good. So first we divide it into frames of using rectangular window, then we smooth it using Hamming window. Now once we get the small frame, then we smooth it using a Hamming window. You can see that we are doing this frame with the we are multiplying doing the element wise multiplication of frame with the Hamming window. So once we do that, we get a small frame which is smooth at the boundaries. Now for every frame, as this equation suggests, we have to do element wise square and add it. So that is what will be done here. We do the element wise square, find, and the output of this will be the frame energy. So with respect to every frame, we get one frame, and we get one value, that is the frame energy. So okay, this equation will be used later. I will explain that part. Okay, now let's visualize it. How is it looking? Like how the energy is how energy looks like over the speech signal. So you can see that energy very much takes the shape of the speech signal, right? Of the like in the regions of the voice regions, right? So this is how energy looks like. Like this is for every frame we get one value, but what I have done is, so to proper make the envelope for the speech, I have done the resampling. I have resampled the frame energy from frames to number of samples. So you can see here, I've taken the frame energy and I have resampled it with respect to, like, resampled it to the number of samples from the number of frames. So this will give the frame envelope, like energy envelope for the entire speech signal. This is how we compute the energy of the speech signal. Now coming to the zero crossing rate. So zero crossing rate is gives the information of number of zero crossings present in the speech signal. Let me tell from this. Let me zoom in here. Yeah. So this is one zero crossing. This is second zero crossing. This is third zero crossing. Like if we start our speech signal from this point. So this is first, second, third, fourth, fifth, sixth. So there are two types of zero crossing. One is positive zero crossing. So positive zero crossing is basically when the speech signal, when the data or the speech signal moves from negative part of the y-axis to the positive part of the y. Right. So that time we call it as positive zero crossing. For negative zero crossing, we have when we move from positive y to negative y. So that is negative zero crossing. So how do we compute that? So there's a well-known technique for that. What we do is we take the signum. Signum is basically when any signal is greater than 0, it should be 1. When it is less than 0, it should be -1. So what we do is we take the signum of the speech and the of a speech sample and the signum of the previous sample and take the difference of that. Then we add those. So we get, if it is 0, if it is zero crossing, then it will give 2 as the value. If it is not, it will give 0. So let's put the values and see. Say it is not positive zero crossing. Say it is not a zero crossing either. Like one of the sample is 0.1, other is 0.2. So when we at t equals to 0, it is 0.1. At t equals to 1, it is 0.2. So here we will keep the value of, sorry, n equals to 2, n equals to 1. Okay. So for n equals to 1, we have said that it is 0.2. So what will be the value of signum? It is greater than 0, therefore it will be 1. So we will keep 1 here. Now for 0.1, here again it will be 1. So 1 minus 1 is 0. So that this will not be a zero crossing, because like when we add it, it will not contribute to the number of zero crossings. Whereas if it is a positive zero crossing, means at n equals to 0, we have minus 0.0, minus 0.1, and n equals to 1, we have 0.2. So we will keep here for n equals to 1. So here what it will be, signum of 0.2 is 1, and signum of minus 0.1 is minus 1, right? Because if for s less than 0, it will be minus 1. So here will be minus 1. So minus 1 times minus 1 is 1. So 1 plus 1 will be giving 2. So we can, okay, so here's one mistake. Here it should be 1 by 2 also. So 1 by 2 into 2 is 1. So that point is a zero crossing. It will contribute to the zero crossing part. So we can calculate that, okay, at this position, we will be having a zero crossing. Similarly, you can, so this was for the positive zero crossing. Similarly, you can calculate the negative zero crossing. When we keep here like minus 1, or then you can keep here 1, then you can see that you can, when you put substitute the values, it will give you 1 or 1 or 0 depending upon the zero crossing. Now let's see how do we code that. Yeah, so we take the speech signal and okay, and resample it. Like this is just a practice, good practice to resample all of them at a common frequency. Now we perform the windowing. So this is short-term processing. Every time we have to do perform windowing. So we have taken Hamming window and performed the segmentation. Now these are the different speech segments. Like let me show if I can run this one. So here, this speech segment has been divided into 358 frames, and for every frame it is 160 values. You can see here L. So we have taken the window size as 160. So one thing I forgot to mention is, like we generally take the window size as if you take the window size as n, we have to take we should take, that's a good practice to take window, that frame shift of n by 2. So that is what we have done here. So after dividing it into segments of speech, we are getting 160 cross 358 matrix. So 160 is, for every frame we will be having 160 values, 160 sample points, because we have taken the window size as 160, and the segment and the number of frames will be 358. Like it comes out after computation. So we have divided it into frames here of and stored it into a matrix. Now for every matrix, like for a matrix, for every column, we will be doing a short-term processing. So we do that now. So let's see how do we perform the positive zero crossing. So as I said, we will be taking two successive speech samples. We will do the difference of that. If the signum, if the difference is 1, then we can, or if it is not 0, we can say that yes, that is a zero crossing. So how do we do a positive zero crossing out of that? So let's see here. What we will do is, we will take the speech segment and we'll find how many values are greater than 0. Just I will run this section of the code. Yeah. Okay. So all the values that are less than 0, by keeping like what I have done here is I have taken the speech segment and found what all values are greater than 0. If it is greater than 0, it will be given as logical 1. Otherwise, if it is less than 0, it will be given as logical 0. So all those values, these values are basically less than 1. That's why they have come out to be 0. Okay, and these values are greater than 0. Hence, they have come out to be 1. Now, to find positive zero crossing, what should be there? The difference of these two should be 1, right? Then only we can say that it is positive zero crossing. Like difference as in how this diff command works is, let me show you. It will take this second sample and make a difference with first sample. So that's why in that way it will compute the difference. So let's take this is a basically a positive zero crossing, right? So it will take 1 minus 0 is 1. So therefore the locations at which the difference is 1, that point is a positive zero crossing, because it is changing from negative to positive. Similarly, if you take this sample, no, the 1 minus 1 is 0. This is not a zero crossing. Now coming to this sample, what it will do here is it will take 0 minus 1. So it is giving minus 1. So it is a negative zero crossing. So that's what I have written here in the code. What all I will just pick the sample values which are greater than 0 and label it as 1, and the remaining will be labeled as 0. The difference, when the difference is equals to 1, it will be given as, and I will find those values, what all values we are getting as at what all values we are getting the difference as 1. So let's see what all values we are getting. Okay. So these are the locations in which we are getting the positive zero crossing: 74, 87, 99, 103, and so on. Similarly, at these all locations, we are getting negative zero crossing. So if you see here, these are the locations, because the difference should be -1. So just you found out, like using this find command from of the MATLAB, we found out what all locations I have the negative have the difference as -1. So those are the locations of the negative zero crossing, and we store it into an array. Okay. Now again, like I will tell why I am using resample here, just to, like as I have said here, just to make it in the show how the envelope is looking like. I just resampled it. Otherwise, if you see, just let me put a breakpoint here and run this part. Okay. Yeah. So you see positive zero cross. So as I have said you that number of frames are 358. So the number of zero crossing will also be in 358, because for every frame we will be getting one representation value for positive zero crossing or negative zero crossing, right? So once now in the next step, what I have done by resampling means, like I just cannot like plot this 358 values with all the number of samples, that is 28,000 samples. So I have to resample it so that I can to this value, so that I can give a picture of how this zero crossing is varying with the with the speech signal. So I've resampled it with the resample command. Just you have to put the function that, or the variable that you want to resample, the value to which you want it to be resampled, and the value from which it has to be resampled. So the variable to and from. So that's how you compute the you resample in MATLAB. Okay. Then after resampling, you can see the values have changed to 28740. Similarly, that has been done for the negative zero crossing part also. Now, yeah. Now, if you see, this is the envelope of the zero crossing. Now, the interesting observation that we should do here is in the energy part. So we know that these are the locations. These locations are the voiced regions, right? And was mostly used to identify the location of the voiced regions. So after seeing the envelope, you can see that at the voiced regions, energy regions are high. Why is it high? Because we know that vowel carries the majority of the energy regions, and in the voiced regions, it's basically the regions where most of the vowel locations are there. Vowel regions basically. So using this energy regions, we can identify the voiced regions. These regions, this region, because at this location also the energy is high. This location also energy is high. So this is basically the regions of voiced part of the speech. Now we have to keep a threshold, right? Above what threshold we should keep, or above what uh, value of the amplitude we should say that the region is voiced region. So generally it's mostly used, not computed. It's an empirical value, like it has come out of experiments, that 0.06, that is 6% of the average frame energy is typically known as, is typically kept as the threshold. So whatever frame energy that you have computed for every frame, if it is greater than 0.06 of the average frame energy, then we can say it as the voiced frame, right? So for those frames, we just store those frames in a certain, you can store it in an array, and you can label it as, yes, this is the energy frame, or you can say that these are the voiced frames computed by this methodology. Now similar, now using the zero crossing rate also we can do that. So zero crossing rate, how does it classify whether it is voiced or unvoiced? So now let's closely observe this one. Okay, so this is a voiced region, this is an unvoiced region. Okay, if you see the zero crossing rate here, let's see at the boundary itself. Yeah, so for the voiced region, the number of times the this signal crosses the zero is comparatively less. Okay. Let me zoom it again. Yeah, so number of times for this is voice region, and this is just a fricative, I guess. Yeah, so this is the unvoiced part of the speech, this is the voiced part. So for the voiced part, you can see the number of times it is crossing the zero, right? It's quite less when compared to this one. Here if I zoom in, see, within a small frame as in small strip, if I take here, only it has crossed it multiple times. Whereas strip of the similar length, if you take it here, it would have crossed one, or even it would have not crossed. Max 1 or 2 times it would have crossed. Therefore, we can use this property of the zero crossing rate, that for the unvoiced region or for the noisy regions, the number of zero crossing rates will be very high. Whereas for the voiced regions, number of zero crossing rates will be quite low, right? So that's what can be seen here. These are the voiced regions, right? So there the number of zero crossing rate is like, of course there will be a zero crossing rate because we are taking a frame of around 160 samples. In 160 samples there will be around 5 to 6 zero crossings. For the unvoiced samples it will be quite high, right? So therefore we can say that you can use this as one of the tool to voice and voice classification. Here if you see, this is very high here. Why? Because it's like completely noisy, like I guess it's a frication or so. So in a small, very small frame, it has crossed it so many times. So that's why I think I lost the curve. Yeah. So because of this unvoiced part of the like large zero crossing, here we are getting such a peak. So this way we can do zero crossing rate using you can use voice and voice classification using a zero crossing rate. Here there is no, I don't remember any thumb rule as we have got for energy part 0.06 of the average energy. I don't remember whether we have for this one or not, but after observation you can keep it, like you can take 10 50 50 60 speech frames and compute the zero crossing rate and try to find the mean of that, like well, the median of that, how many times you're getting the perfect voice classification, and you can keep that as one of the threshold. So now combining uh, now let's officially explain voice and voice speech detection. So by the nature of production, the speech consists of voice and silence regions. So energy associated with the voice region is quite large compared to the unvoiced region, and silence region will not have will have negligible energy. Thus, short-term energy can be used for voice and voice classification. In case of unvoiced sound, in case of unvoiced sound, the ZCR is significantly high. We have seen that, and it will be significantly high when we compare it with the voiced region. Now, combining both the evidences at one place, let's see how both give the whether both of them align together or not. Yeah, so we can see here, right? So the blue one is the speech signal, uh, the brown one is for the energy part, and for this yellow is the zero crossing rate. If you see this region, this is unvoiced. Here, for the according to observations that we made before, for unvoiced region, the zero crossing rate should be high and the energy should be low. So that is what we are getting here, right? Energy is quite low and the zero crossing rate is high. So both of them aligns. Whereas for the high energy regions, zero crossing rate is low compared to this. If you see these ones, this one, it has reached up to the value of 0.6 or high, but here it has not. Here energy is also high and the zero crossing rate is also low. So therefore, we can say that this is a voiced region. So both of them aligns at one direction. So this can be used, these two can be used as a feature to classify voice and voice. So that was for the time domain processing. Now coming to frequency domain processing. So there are two ways. One is narrow band and wide band. So narrow band is basically when we keep the narrow band. How do we say? Why do we say narrow band? So band means number of frequencies that it is acquiring, right? So if it is narrow, means if it is capturing less number of frequency in the frequency domain, it will be known as narrow band. And if it is capturing large set of frequency in the frequency domain, it is wide band. So we know that from the we're taking support of the DSP part, digital signal processing. When we have small window in frequency domain, we have larger window in time domain, and the vice versa. Like if we have wider window in frequency domain, we have smaller window in time domains. So that is what will be used. So we do perform short time Fourier transform, and what we do is okay, this is a normal spectrogram, like without any wide band. Like we have taken the somewhat window length between the window that we select for wide band and narrow band. So this is the ideal spectrogram that we can say. Now how the wide band narrow band affects. So we have taken here 160 as the window length, and the overlap of like 80. As I said, ideally we take the window length by 2. And here we can see that when we take narrow band means it is narrow band in frequency, means narrow like you can say the less number of frequencies we are picking in the frequency domain, which means we have to keep the time domain window big. So we have kept it here as 320 and computed the narrow band. So here you can see that compared to this one, it has the band here is quite, like compared to this spectrogram, there's less, the band is quite small here, right? The width of the band is quite small. Now coming to the wide band spectrogram, here the width of the band is quite large. You can see it has captured much well the spectral characteristics, the formant locations, you can say. So it has captured well, but here you can see that it is dispersed because it is capturing large band in the frequency domain. And also we know that in narrow band we have kept the window size large, therefore in the time domain it will be capturing large information. So you can see this band here till here to here, this is one window. From here to here, this is second window. From here to here it is third window, and the fourth and fifth, like this. Whereas if you see the wideband, very tiny, very thin strips are made here, which means that if we want to capture more resolution in the time domain, we should use wideband spectrogram. You can see that there are very tiny strips here. The width of the strips are very small, which means more resolution will be there in the time domain. Whereas if you want to capture uh, more resolution in the frequency domain, you should use narrowband spectrogram. Means it, as the name suggests, narrow in band. So narrowband spectrogram will be used for capturing, if you want to capture more frequency resolutions in frequency domain. Yeah. So so there's a trade-off. Like if you want to use more, then you can, like, according to your end goal, you can use wideband or wideband or narrowband. But ideally, we use this one. Like this captures both of them. Like this is a trade-off basically. If you don't want to lose any of the information, you can take a middle path, and you can keep a window of 160 to perform this, to generate a spectrogram. Yes. Okay. So yeah, we are done for the tutorial. So any questions? Hello.
Ayush.
Yes.
So there is a question, I think, in the chat box. You can respond to that.
Okay. What will happen if you take frame more than 50 millisecond or 100 millisecond? Okay. So as I said, speech signal is stationary within a frame of 10 to 40 milliseconds. So a non-stationarity will come in, right? So we'll not be able to accurately determine the frequency. Like we will not be able to accurately apply our signal processing toolkits there. So that will be the major issues. So if you want to extract information at a segmental level, that is in the frame of 10 to 40 millisecond, then you should be using that frame. If you use more than that, you will be extracting more of a supra-segmental information, like the prosthetic information and all.
Yeah, let me clarify that point. No, actually, the short-term processing, what actually 10 to, it is assumed that from 10 to 40 milliseconds, it has some kind of stationarity. So you can go and do some signal processing operations on that. As it is like rightly mentioned by Agnanarana sir in previous lectures, that the speech signal is the convolutions of time varying vocal tract response with a time varying excitation. So the output is also a time varying signal. Okay, so that is why it's kind of non-stationary. So if you take 200 millisecond or 150 millisecond, it will, again, you will able to see the spectrum, but it will just an average version of that. So you can't get the exact variations what it is happening with respect to time. Okay, so that is why if you want to know the actual spectral variations, you can use the short-term processing to see the variations with respect to time. So that is the answer. If you have further questions on that, you can we will take the questions. So I think another question, can you mention one application of narrowband spectrogram? Ayush.
Yeah. So as I said, like as an application, when you want to analyze more in a frequency, like you want to you need more resolution in the frequency domain, you need to use narrowband spectrogram, right?
Maybe one possible applications what is coming to in mind, that maybe the pitch estimations you can do it. Yeah, vowels also can be analyzed, and
yes,
pitch also you can estimate. Okay. So another questions, after framing using humming window, what is the need of smoothing using humming window?
Okay, no, I am not doing that. I'm not doing that. First, I am not using this hamming window and then Hanning window. I said we have done the framing. using the rectangular window, and since it is abrupt change at the boundaries, we have to smooth it using Hamming window. So we are not using Hamming after Hamming. We're just using Hamming window over the rectangular after we segment it using rectangular window to smooth it at the boundaries. Yeah.
Okay, fine. Any other doubt? Okay. There
Okay.
have no other questions.
Ayush,
Yeah.
can I add one point?
Yeah, definitely.
Yeah. Now that you are showing the narrowband spectrogram, can you just compress it? I think you have enlarged this, right?
Compress it as.
Oh, okay, let it be fine, no problem. So when you are seeing at the narrowband spectrogram, all the yellow color lines you are seeing, they are called harmonics. Okay, and similarly, can you once show the wideband spectrogram?
Yes.
Yeah, these yellow color lines you call them as formants. So these can be used for extracting narrowband spectrogram characteristics are used to extract the either fundamental frequency or in terms of time domain, if we say it is called as pitch, and in the wideband spectrogram it is used for extracting the formant characteristics of any speech signal. These combinations, depending upon any task we want to perform, combination of these characteristics are used. Whether if you want to perform voice activity detection, only narrowband characteristics are sufficient. Maybe depending upon the types of noises also, it might differ. So in such cases, you will have to combine both narrowband characteristics and wideband characteristics and still try to identify voiced or unvoiced, because the noise is corrupting the two characteristics. Okay, depending upon the type of noise, it may corrupt the characteristics in a different manner. So you will use either wideband or narrowband to extract those speech characteristics and identify the speech regions. Likewise, if you want to do speech recognition, means which sound is pronounced and such things, then mostly narrowband characteristics are used. Suppose you want to perform speaker recognition, who has spoken or such things, then more priority is given for wideband characteristics. At saying that, uh, it is also important that both characteristics correspond to both the speech specific content and also for speaker specific content. You cannot discriminate, like because someone is asking for application of the narrowband or wideband characteristics, the combination of these two things are used mostly. You cannot discriminate that this can be used only for this or that. Okay.
So thank you. Maybe with respect to your applications, you can see how you can analyze with respect to different spectrogram versions. So it's all about today. So if you have further questions, you can ask, or else maybe we meet tomorrow at 10. Okay, fine. Thank you, Ayush.
Thank you.